Go ahead and begin. So our first talk is going to be from Shreyas, talking about workforce development and getting ready for the quantum impact, for the future quantum impact. So please take it away, and questions are welcome in the chat boxes and Q&A, and I'll try to relay those along the way. So thank you.
Hey, thank you, and welcome everybody who have joined today. It's definitely an exciting topic. You would have heard from a lot of other esteemed colleagues and of mine, as well as friends who have spoken around the actual hardware and the way in which the quantum computers can work and the software side of things. I want to relate this thing back to how to get ready to start planning and experimenting. Now, planning and experimenting to getting ready for this journey is what makes it super interesting. To start off with, preparing for the quantum future stands to be definitely the most disruptive. It's seismically disruptive. It's huge. The way how impactful it is. Yeah,
hey, Shreyas, you are cutting out a little, so maybe let's use the phone if you can.
How is this?
Yeah, just mute yourself on your video or on your computer, and then we'll be good.
Yeah, I don't hear you.
All right, I had to push *6. How about now?
That's good.
Yes, I hear you now.
Awesome. Thanks, guys, for letting me know. So there's definitely 4 key steps to how we perceive to accelerate your journey and the enterprises whom you're actually going to wind up working for eventually. Enterprises are research organizations within your universities. First and foremost, which I think most of us over here, is what can quantum do? I think we all know what quantum can do from a physics standpoint, what quantum computing can do from a physics standpoint, and how to go about developing applications or your own Jupyter notebooks and your experiments. We're experts at this point. We know the technical side of things. Now, we want to know how and where that applies to your business. Your business being where you end up going to work eventually, whether it's from a research standpoint or just general, any companies that you wind up working for. And as you're doing that, we'll talk a little bit about what that looks like. And then we'll talk a little bit more around using that and building your story and creating this innovation roadmap. It's important to know that you have to have some kind of a grounding or a plan to do or executing something. Either you come in as a managerial position and you're at the point where you're building this thing up from the ground up, or you're a developer or someone who's on the ground, and I'm going to talk a little bit more about the different types of people who will be involved in the quantum project to build that roadmap. We'll work with hardware up until this point in time. You'll work with software up until this point in time. I think this group over here knows that you can pick and choose which one you want, and it's obviously going to depend on the type of case that you bring up. There's no one shoe that fits all, one size fits all. So whether it's for hardware and software, or even from a talent perspective. So we're going to kind of build the story today across these different layers and generate this workforce of this future. We know that the impact is here today, right? You would have seen this in all the previous talks. These numbers are staggering, right? As of right now, according to Tractica, the spending on quantum computing is going to surge in the next 10 years. We're already at roughly about $260 million worth with whether it's cloud revenues or services revenues. That number is going to go to a staggering amount of $9.1 billion US. That's quite a lot. And we know the different kinds of approaches that will yield this. And typically speaking, and you would have seen this in the past conversations, you go the analog approach of quantum computing. These are your gate models and how, the superconducting qubits, et cetera, they all kind of mesh together. Then you have the digital route of doing this information that's processed by a quantum algorithm. Fujitsu is a classic example. You have the quantum-inspired approaches that people like, QIO, Microsoft. You just heard Microsoft talk about this yesterday. It's super exciting that they're especially designed for this in order to simulate what these quantum mechanical phenomena occur, that you can actually apply your solutions today for tomorrow as well. And we know that typically speaking, you would have seen this before. We think about these problems as optimization problems, machine learning problems, sampling and simulation problems. And just to kind of put this into some context of how you do these things on a day-to-day basis. I want my Amazon delivery. I'm not saying Amazon is using this for their route optimization or any such thing, but when you think about optimization, you're thinking, okay, hey, I want my package to be delivered from point A to point B. But as a company, it's not just my one package that's coming in. It's the collective. Everybody who's here on this call may have ordered a bunch of things and want to make sure I distribute all of them properly. That's a very difficult problem to solve. And you know this. You have machine learning types of problems. We've all heard about feature mapping, solving linear equations, clustering, regression, etc. You relay this back into how the fields of application are there for the use cases in mind. Things like, I want to figure out if the passport that I'm scanning is the right person that I'm scanning. The image in the passport isn't going to fool me, that there aren't any perturbations in the image itself. There's only certain limitations. You can obviously do all of these things classically, I'm not saying you can't, but you're going to run into a juncture where these sort of classical solvers will wind up hitting a limit. And so this field of application in quantum exists as well. Sampling and simulation. We have experts in the chemistry side of things. How can I figure out these two molecular substances? How are they going to interact with each other? What do they do? How will they further generate something new? So these are some of the questions these fields of applications are going to help answer. If I were to explore all of these things, the current mindset that most enterprises wind up having is, let's go from a bottom up, because technologies oftentimes they're working with are not as fresh as quantum computing. And R&D cannot follow the same exact path, right? You can do this thing in a very mature, sort of fully industrialized solution, but the current norm of this R&D industrialization is simply doesn't cut it, because you wind up missing, don't make the business case to actually happen. You don't have the vision to actually make something happen. So one of the things that we want to kind of shift the mindset is, from a business standpoint, think about it from a top-down perspective. You need your C-suites, you need your overarching economic buyers who are like, I want this to happen. I've got the US government or the Chinese government or different entities, different countries thinking this is super important. So this is not necessarily just true for companies, but this is true for anyone, academic, businesses outside, public or private, and your governments. You need to have these things baked into mind where you can actually run and innovate at scale. And we all know this is there at the cusp of everything that we want to have happen, but it's not quite there yet. When you ask people around, and we did this, and we looked at from Gartner's perspective, you know that people want to have this happen. And we know that in order for this to happen, even though that 90% of people are saying, I'm going to make it happen somehow, there's still certain hesitancies in actually executing it in that same, this new way of exploring quantum. This whole top-down approach, this industrialized approach to making it happen. It's not just me who's saying this. So when I take a look at quantum, and this is a study that was done by IDC, we knew for a fact that 65% of them felt like, yes, we're going to go through this because we love it as cloud computing. And we know that quantum algorithms are super important for us, but not quite. It's not that I'm going to do this myself, but I just want to have someone provide it for me. We knew that people want to understand it from a network and a sensing perspective. It's important to them, but not necessarily as important as the other two items that I just articulated. Hybrid is coming up very quickly right now. We knew that quantum computing, universal quantum computing, meant the way it was done before with the superconducting qubits. Now there are so many different ways to go about it. When you want your near-term benefits, you simply turn to the optimization problems that hybrid quantum computing essentially can provide. Vendors like D-Wave provide this approach. The QIO, the quantum-inspired approach, is a similar fashion as well. Don't take my word for it, right? There are people who are actually doing this thing right now, not only those studies, but there are actual people who are companies, and the people in the companies are actually doing this. They're super mature companies like Biogen. It's basically, they ran a series of experiments, and they found out how to do molecular similarities based off of the drugs that they want to have designed and then executed and then built on from an Alzheimer's perspective. BBVA ran 3 different use cases to do exactly the kind of stuff and experimentation that they wanted to have done, leveraging hybrid computing parts. There are so many other great people at JP Morgan Chase and the VW group who are really kind of pioneering very well from a company standpoint. So they've actually got use cases that they've developed and they've done. It's not just the traffic flow, it's the paint job, which is a job shop scheduling type of problem. Super important. Governments are getting into it as well. And to kind of tie all of this back up to something that is real, we want to fast track this stuff. We know we want to kind of gain an overall understanding of these things and how they work, but eventually you want to develop a plan to improve any kind of business level acceptances and the organizational readiness for anything that you want to have happen. And you know what? We're going to talk about exactly that today. It sounds like, hey, how can you push all of this stuff into 4 easy steps? Oftentimes, that's where we wind up going. These might eventually just be these 4 easy steps to look into. Step 1. Learn what quantum can do and decide where it applies. Now, we're used to learning what quantum can do just by, let me pick up my Jupyter notebook, let me pick up some Python code and quickly run certain bits of algorithms. I have a series of ideas on how to optimize XYZ for this R&D project that I have. All the right answers from an academic perspective in order to get and understand how quantum works. We want to make sure the quantum can solve these problems. Definitely, we're doing that. That was once taught in tractables, these NP-hard, these NP-complete problems, which is what quantum is expected to do. And it's set up to, is designed to actually have happen, which some instances do actually happen in those previous examples that I showed you. And we'll talk very quickly about how you go about identifying and prioritizing these problems, figuring out what are going to be your limitations in doing so, the challenges, I would say, and strategically. You got to be very strategic about choosing the right use cases. It's important because it's not to say that I want to solve the world, I want to solve, climate change, for instance, solve for climate change. Well, it's great. Let's get into a little bit more detail about what it is that you're trying to do over there. What are you trying to understand? So anyway, and even with that, mathematically, is there certain formulations that you can kind of set to set up certain objectives, constraints, etc. from a linear perspective? Gate models, how you choose the problems is going to be slightly different. We'll talk about that as well. Figure out exactly what it is that you're going to compare this niche use case to, and find out what these quantum algorithms can actually use to solve them. So a lot of people who've done some incredible research on it. Can you apply something that has already been done? Do you think you're going to write your own, which is also the right answer? You can kind of use your own perspective to do a long-term research project with a company. And mind you, people will absolutely do that. You can't actually execute all of these things yourself. You still need to have the people and vendors and your partners to back you up. Whether it's IBM, whether it's Microsoft, whether it's D-Wave or AWS, you have options that are out there right now, but you pick your use case, pick this journey that you're going to go with, and explore this. Now, I want to talk to you a little bit more about these 7 steps, and I'll kind of walk you through very quickly in how you are going to actually go about doing this. And I'll pause very quickly as I get to this page, we kind of give you this example. What's actually worked tremendous for us at Accenture, and it's keeping it simple. It's a complex problem. It's a problem that we don't quite understand. No one understands quantum yet, but we do understand these use cases. So let's try to keep it simple. Let's find something that you use or you plan on using, whether it's your business, from an academic perspective. Let's talk through it a little bit more, right? So if you were to just, your past experiments that you just ran in the previous sessions, you had something in mind and you were experimenting with it. But let's pause for a second. Let's talk about what it is that you're trying to solve for. Give it some concept, give it some meaning behind it. And I'll pause over here before I talk about some of those immediate examples that I think we can kind of get into. So do we have anything on the board right now as far as questions? I'm sorry, I can't really monitor the chat window.
Hey, yes, I believe we have a few questions in the Q&A that I will just read out loud.
Sure.
The questions are from Graham Jacobson. How can we approach businesses and consulting when many aspects of quantum are still in the research phase? And question 2 from Pei Wen Tsai. Is there an estimation on a time when the quantum use cases will be realized?
The best question, okay, the second one was one of the best questions that almost every client asks, but I'll answer the first one. How do you approach this? Well, you start with this page that I'm showing you right now. You start with an idea. You start with a description of what that idea is and what it is very specifically that you're trying to solve. I'll give you this example of portfolio optimization. You've heard about this. You've got bankers, hedge fund managers, and risk portfolio managers, whomever you have within the capital markets industry. They're trying to make money in some way, shape, or form. Now, to be pragmatic, to be objective about how you wind up making money, there are people who have created classical formulations. I think this was back in the early 90s. I'll give you this example of someone from the early 90s that kind of inspired us. Bert Smith, Susi, and Darnell from the 90s, early 2000s wrote up a paper on how to go about optimizing or rebalancing the series of assets within a portfolio that a portfolio manager does some stuff. We knew that it's so complex out of some series of objectives that you want to solve for. And it's the right thing to kind of include these different soft and hard constraints for these different objectives that you attach it to as part of your equation. But these problems, we knew it's a super hard problem because when you're trying to optimize these series of assets, now imagine that you're trying to optimize which one do I pick within the S&P 500. You can have 512 different assets. If you pick up like something like NASDAQ or the Russell 2000 or whatnot, you have the number of assets just exponentially increases. Now imagine number of assets multiplied by the series of variables that you're constraining yourself to understanding what to pick based off of a certain set of guidelines to make sure that you're actually getting alpha back at the consequence of it, at the tail end of it, while still mitigating the risk associated to it. That was done on a linear fashion. Well, we're like, from a quantum standpoint, like, well, heck, why can't I just do it at once? Why can't I create one of those polynomial or a quadratic form to solve for this? I think that's exactly that's an exact type of use case, how I would go about approaching it. So I would start with something like this that said, let's create an approach to solve for a problem. Let's attack its very, very minute pain point. And let's try to get into, if there are any existing papers, then we'll work through some time to formulating the mathematical form and the functions and so on and so forth. But you start with that. And to your point on, well, when am I going to see some realizations in this? What was super cool and interesting about even this, the same financial services use case is it wasn't like it solved it significantly faster than the classical solutions, but it gave you the opportunity to solve something that was complex in a single hit, in a single run, using similar anneal-based technologies that eventually hit a hybrid system that could actually use or compute against multiple different variables. That's a good way to kind of go about it. Now, how quickly is it going to happen? Well, it's a tricky question, right? Like when you have like 50 to 60 or 70 different assets that you're trying to rebalance at any given point in time, you multiply the total number of variables that you're using, etc. You quickly near up to about close to about 8 to about 10,000 different binary variables that you're going to have to map to a quantum system, which is mapped essentially from binary qubit kind of a perspective. So it's not like we could immediately do it. So you reduce the size of the problem in order to solve for it. And when we solve for the problem, it actually solved pretty damn effectively, because we were actually able to show and demonstrate that it was roughly 1.2 or 1.3x times what S&P returns were traditionally, had you done these exact same, based off of some 52 weeks of back testing of data in there. And to that point, chemistry has something that's a little bit more unique in that nature, where it just allows for mapping of how the gate-based devices just automatically leverages the properties of physics, that you can just essentially understand how these molecules interact with each other. Similar story. And the result that you're going to get out of that one, it's not immediate. We're still kind of working in finance and in fine-tuning that stuff. But just to give you a glimpse of what it is that I just talked about, I think this is exactly what I was telling you about, as far as keeping it simple and how you chart out that plan, is to make sure you have the description in mind, the same description that I showed you in the previous pages. It's simple, right? Just a simple sheet that I have. That sheet grew into something more, which is defining the problem, creating a mathematical potential approach to it, creating any problem reductions as far as you wanted to have as a consequence, and then actually running it against a software developing kit. Whether you wind up using D-Wave because you found the optimization that Hybrid provides over there is good, or the Microsoft QDK stuff that they provide for the QIO to kind of tap into the QIO or 1 qubit, parallel tempering or taboo solvers that they have. It gives you the flexibility to tap into any one of those things at that point in time. But again, keep in mind you're solving a business problem, and that's the pathway that we're taking over here. And just to quickly pause over here, or rather, let me wrap it up. So define a plan, get those use cases in mind. Now incorporate, so as you're building these things, bake this into how you're actually tapping into some of the long-term value propositions that this essentially provides. And as you're building this plan, let me quickly talk to you about this plan from the standpoint of how you think you're going to create a certain impact. Let's just assume right now, the impact over here can be a dollar amount impact. It can be an impact in the market, like you're doing something brand spanking new that nobody else in the world has done, and they're going to see like, oh, right? It's great. It's a research type of project. It's going to be mind blowing. You take the same sheet that I just showed you previously with the description and the pain points, place it on this map. How do you think it's going to impact? And you obviously have more than one idea. So where does that stand in relative to the previous? You're going to have more ideas as you're building a business. Where does that stand in relative to the next one? Makes you think, as you're building these ideas, you're creating more perspectives into where you think you're actually going to create something of great value eventually. You know what? I'm sure that everybody's saying, hey, you know what, this is great. I can easily put this stuff together and say how much value each of my ideas are going to bring in relative to the next one. The exercise is super interesting because the next step that you're going to do is, how easy is it? Is it something that I can achieve from a feasibility perspective in a low amount of time? Is it going to be a 3-month project? Is it going to be a 1 month, 3 months, 6 months, 8 months, 12 months, 18, 36, 48, whatever. Keep whatever number you want based on the ideas that you think you're having over here. And then let's move them. Let's move them up to its respective areas. And as you go about this process, you can be doing this from an individual perspective, just by yourself. You can do this thing as a group of people within your team and kind of placing this on this sort of a 2x2 matrix to understand what projects are going to happen. And guess what? Very clearly, this top part over here is going to be the project that you're going to start most likely. Something that is very feasible, aka it's not going to take a lot of time, or it's going to take a lot of time and I want to actually do this. Depends on your priorities. I personally think it's feasible, that it's highly feasible to do it right away, or it's highly feasible because I have the formulation, I have everything in mind, I have a plan in mind, I can execute it. Experimentation is going to take a long time to do, but I know I have this vision and I know it's going to make a great impact. Target this, put this in a continuum of near term. I can tactically do these things right away as part of my first projects. Medium term, I want to kind of do it. I know I can do this stuff, but let me have a couple of thought process around that. And then eventually all the low-hanging fruits that you know are not going to be feasible, or definitely ditch away things that are going to be low feasibility and low impact. And this is just maybe like a very, very low level type of problem that you yourself are trying to solve for. It varies as an example. So start with this, and this is going to help you put the stuff on a continuum. Next, evaluate your hardware, right? We've been around this boat before numerous times because we knew exactly which one to pick, which use case to pick, and how to pick these use cases. So if you recall on one of the papers, and I'm going to take you back to that paper, and I'm going to come back here again. In here, you selected the type of problems. The type of problems will give you the idea or the notion of what technologies are most relevant for it. At least in my own opinion, when I think optimization, I think for near-term purposes, the annealing, inspired, and hybrids can solve the problem. Not that the gate can't solve it. It can. The size of the problem that you're trying to solve for is going to be smaller. But you know what? There's definitely promise that it can solve something much better as the number of qubits and the fidelities for these things improve. Just to give you that, tie this back to what I showed you previously. And as you're evaluating these things, know that you have options, as I mentioned before. Think in terms of, the Rigettis of the world, the IonQs of the world, the Honeywells of the world, the IBMs, the Microsofts. Microsoft have multiple different options. Many of these things are available in the cloud that you can tap into at any given point in time. And you can use it. Align with a very specific use case in mind. Again, those use the same exactly as before. Work with an agnostic provider if you can, possibly, so folks like AWS and Microsoft Azure, they provide the means to tap into multiple different hardwares. Not that you can't go directly to the hardwares, but you can. So to wrap that section up and quickly coming very close to how I can you use all of these things to build up on where you want to go. The partner that you're going to help with can accelerate the journey because oftentimes these partners have either snippets of codes that you can kind of implement at any given point in time to explore things that haven't necessarily been explored, or they can give you quick access to the devices itself that you oftentimes would just have to go through a series of processes that you don't need to go through. And you can even start programming with any language of your choice, right? Like you've heard this before that Microsoft or you're working with their QDKs. It's not that you're 100% tied to leveraging the Microsoft text as far as C and C++ or Q Sharp, you can use Python, right? It's universally available, and a lot of these vendors give you that flexibility to do so. What's really interesting, and this is the last part, is super important. It's a lesson learned from a couple of different places that I worked at. The company that you're working for, or the academic institution, or the government institution that you're working for, need to be amenable to working with the infrastructure that's going to support whatever it is that you want to do. It can be whatever you want. Fine. Now that I have all these, and there are definitely two skill sets you need to stay aligned to the goals. You know that there's certain aspects of things like machine control, or assembly languages, programming languages, and the libraries that these people kind of wind up developing. And from a development standpoint, on the right-hand side, these are your companies, your firms, your companies like the Biogens, the BBVAs. They care about what are the applications, what are the APIs, what are the products. Accenture typically likes to work on the right-hand side, more on the right-hand side of things. If you want to cut it right where the blue line is all the way to the green line, that's where we like to work with. But there are definitely opportunities to kind of work from a machine control standpoint. These actual hardware vendors, they know they need help from a machine control standpoint in assembly language. The providers, quantum providers, are where those types of skill sets wind up sitting. And you probably are going to be the best fit for any one of these things across the entire ecosystem of different talents that you're going to wind up developing. But always keep in mind, this is the important part, like these are the different kinds of talents. Like in machine control, it's like how do you create global local optimizers specific for the machines? How do you control the microcontrollers? From an assembly language standpoint, like how do you get to the more elementary level of getting that assembly level code to be compiled so that the programming languages that you're developing, the libraries that belong to it, can actually give you something of meaning, of essence, of value. And then you can build your own custom libraries that tap into these programming languages by yourself, which very interestingly enough, and I love this about like every single vendor ecosystem that's out there, whether it's Microsoft D-Wave or some of the AWS components, you can co-develop a lot of these things with them. A lot of these guys have open source, and IBM, they open source all of these things. The Qiskit is a classic example of that. I use this thing constantly for a multitude of different things in different projects, and I just absolutely love these things. So very quickly, you have these types of different skill sets. I'm going to tie this really quickly back into the actual application that you're going to build. You still need to source the development, the quantum talent, if you may. And just as you had the simple the concept name before, and I'll quickly pause over here before I go to the next page actually as well. Before I talk more about this page, and you can view this page while I pause. Do you have any questions from this in that front as far as the journey that you have taken so far in plotting it into a continuum, a 2x2 matrix continuum, all the way to where we are with the types of people who work across a continuum of different types of skills needed for different types of jobs. Any questions?
There don't appear to be any questions in the chat or Q&A right now, so I think you can.
Sure. Cool. All right. So in this journey that you're taking to source your your talent. The types of people involved are a lot, right? You're trying to develop something of great value. Obviously you have the concept name that you're trying to typing up, the same description that you had. Who is actually going to use this, and why is it so important for them to use it? So this is a version of a canvas that you're trying to make a strong business case. To the earlier question, I believe was asked by Graham, I believe, like how can we approach them as well? This is about metrics. This is about value proposition that you're bringing to whomever it is that you're bringing to. Whether it's the professors that you're saying, I want to do this piece of experiment, or a board of directors that you're trying to convince to say, you can perform these experiments, and here's when you're going to actually realize the value. The value realization is over a period of time, but here's different types of elements that you're going to realize. What are those metrics? How are you solving these things? And who are the people that I'm going to be involved? Typically, yeah, sure, you have a primary investigator, you might have a project sponsor from an economic standpoint, a lead, people who work on the scientific compute side of things, like from an AWS standpoint, if you're tapping into the HPCs or the QIOs, who's that? From an IBM standpoint, who are the people, the experts that IBM already has as part of their development teams, the ecosystem that they have. If you follow the Slack channels, whom can you involve as a part of this project? And draft off very quickly in simple categories. You can have a start and finish, sure. The timeline that you're going to do this, like I said before, can be in months, can be in years. Well, hopefully it's not 10 years that you're going to be doing this on, but you could. You want to be mindful, like when you're splitting this piece of work, you're still going to split it by what you've researched and have a go, no go, what you're solving for, which you might do at the same time as what you're doing from a research standpoint. How long is that period going to take? Who's going to be involved? So think about having the screen and just kind of putting down very roughly the type of skills that you're going to work. And eventually, guess what? You're going to be able to create a very, very long roadmap of workforce that you have just made a good, strong case for. And it's these quick 4 steps that allows you to do that. That's what makes it super unique in doing it in this manner. And I mentioned before, right? So you have different people with different types of skills, and people from the front end standpoint. I'm not saying use React or Angular, whatever you want, right? You can use whatever you want. Back end services, again, doesn't have to be Node. You can use whatever you want. You use your quantum data scientists to build those pre-existing algorithms, so this new algorithmic ideas that you have them design it from a rough perspective. Find a way that this other person who's actually going to be coding up the back-end series of services. Sure, the quantum data scientist or information scientist can do that. No one's going to doubt this quantum info data scientist to do that from a back-end perspective. But a quantum integrator, you got this software developer kind of a personality who is basically building these things up from the ground up and integrating it with whatever the back-end is. Your back-end developers, these are people who know how to create a database to store these the results, or to store the actual information that needs to be delivered. And you've got these people, the same scientists who will figure out the same question on like which of these different devices am I going to use, parameterize this. It's super important. It's very, very important to know and not skip out on how you parameterize the calls that are going back to the quantum computer. Because I've found out very clearly that by default, just using whatever these providers provide isn't going to actually cut it. You're going to have to fine tune your solutions, the problem that gets sent into the quantum computer itself. And obviously, you're going to have the same quantum information. Our data scientists will work with the computations and the different folks just to give you an idea. This is how we derive those different buckets of things that are out there. If you want to think that middle tier, right? These are your 1 qubits, your forest, your lead from D-Wave, Q-Shop components that Microsoft provides, Circ if you wind up having access, PennyLane, KitKit, StrangeWorks provides different tools, Xanadu provides these different tools, Zapata has an incredible system that you can kind of tap into. with multiple different vendors, their ecosystems. Again, these are all part of the various different choices that you basically have to tap into and leverage at any given point in time. And you know, it's not that you're going to use all of these different options simultaneously. You're going to use some at certain periods of time and the others other periods of time. So now that you have that business mindset on how you're developing your workforce and what it is that you're doing, you also need a way to say, either I bring in you experts who are on the call right now, find a way to skill all of you in relation to the company that you're working for, or the institute, or the government organization, or your own universities, whatever the case is. Or you reskill whom you have right now. There is a journey to whatever it is that you're doing. Think of going up the escalator to the store in a mall that you want to achieve, right? You have different skill sets, different people. You might have a discussion at the very beginning to say, hey, where do I want to go? Where do you as a person want to go? Your advisors. Start from that perspective. There's a lot of self-guided learning tools that are out there right now. And you can find these things online, left, right, and center. You can even YouTube half the different, in fact, almost most of the lectures right now are available online. Coursera has different options. For you guys are awesome at providing some of these different trainings that are out there that we use. There's a lot of tools that are out there, assessments that you can kind of figure out who you are from a skills, from a behavioral standpoint. There are definitely, you know, this sort of an environment, these exact sort of environments where we have large videos of skilling stories and seminars that are being hosted to understand these things. There are definitely job aids that you can kind of self-learn. And what you are as a company or even as an institute can wind up doing as well, right? You get these certifications. As students, you're going to get a certificate from the university and a credential associated to it. That's going to help make the case of becoming job ready. In a company, a company builds their own series of certifications. External companies like IBM provide additional certification badges to showcase how awesome you are. And these are the different pathways that you as a company, or you as a person who might wind up owning a company, or you as a person within a company will go over a period of time. And there's a lot of deep, minutiae details, information over here that will be of value. There's a different deep dive section to all of these things, but just keep that in top of mind. To quickly, almost nearly conclude, remember, the journey starts right now. But in order to do that, you follow the same 4 steps that I laid out before. Look to build the multidisciplinary team that I mentioned before, with scientists, architects, delivery leads, industry experts, to create something that is going to be of value right away. There are definitely blind spots in each of the different skill sets and tools. And the best way to keep all of that in a good step is to ensure that you all, the academic, Purdue as an institute, or other businesses, keep their strategic objectives in mind. Everything that you're learning today is going to help build that future for these companies or institutes or your own government organizations that you might wind up working for. Consider the flexible talent plan that you might have, but if you use that external talent, make sure that they take a reusable approach, just like what I mentioned earlier on. And to kind of conclude that last slide over there, invest in any sort of industry development training programs that are available within the employed locations that you might belong to, or within the academic institution that you belong to. Use it, because the learning never stops. And you would have heard a lot of professors say this before in the past. No one actually understands quantum computing, man. Nobody actually understands it, right? You're trying to understand the best as you can to apply it to the use cases that you know it'll be relevant for. To quickly conclude, disruption, it can happen overnight. It can happen right now. And it's not just me that is saying that. We sent out an interview, we sent out a survey across multiple different people across New York City and New York and this entire region, as well as different regions. And 97% of people that we sent the survey to, who are all C-suites in this entire area that I live in right now, in the Eastern Seaboard, they said that it will definitely provide enormous growth for their company. And I think that you are all at the best place to provide that expertise needed to have to happen. And like I said, have the business mind in your top of mind. And guess what? You can actually disrupt this entire ecosystem overnight, tonight, over the course of the summer school. Thank you.
All right. Thank you, Shreyas. I think we have quite a bit of time for questions or discussion. So for anybody who may have had their hand raised earlier, please feel free to jump in, or the floor is open.
Hey, Shreyas, this is David.
Hey, David.
Thanks so much again for your talk. For all those out there, please post questions in the chat. Unfortunately, with the number of attendees we have and that were registered, we couldn't just have the floor open for anyone. But I just wanted to kind of jump in and ask you, sort of on behalf of students here. You talked a lot about sourcing and developing talent. As an employer looking to hire, students, what, other than, you graduate from a great university and you have a bunch of papers, what stands out to you that's going to give one, potential candidate a leg up on somebody else?
I would say narrate your story effectively. It's not about asking a lot of the trick questions like, hey, how many bathrooms are there in New York City, right? I would never throw such questions like that. It's like, how are you going to solve a problem that you know that you're familiar with? Or how are you going to solve the problem, and how did you solve this problem effectively? It's very important. The more common colloquial is the STAR methodology to going through an interview process. Be that storyteller that you all are, that you all have been training to be doing all this time. And yeah, don't get me wrong, coming out of Purdue, it's a huge thing. It's a big leg up. Doing these awesome papers, definitely awesome, big leg up, credentializes you. There's more to that. And this is what I would start off with. Personally.
Just a reminder, the chat is still open for questions. And I suppose in the meantime, maybe I'll ask a question as well. So, Shreyas, I'm on the, quantum scientist, at Oak Ridge side of things. I think you showed a lot of, how integration works and can work and given some pre-existing environments. What else can the people that are seeing it from my perspective, how can we add to?
So let me see if I can try to answer this question. From a lab perspective, you guys are doing awesome stuff. Right. I tend to learn a lot from all of you, what you've been. The exploration of building your own workforce as it relates to what everybody else in the rest of the world is going to use is going to be of tremendous importance, right? This kind of goes back to delivering something that a business will wind up using at some point in time. The experiments that each of you are conducting right now are, like, I use it all the time. It's awesome. And I would just say the one piece of information is, let's find a way to kind of tie this thing back. I think having the expertise between, academics, the vendors, and the actual companies itself, the businesses, the impact that this provides is monumental. It's incalculable, because eventually, that's where you're going to find a point where the people that are being educated right now and the people who are already educated in the companies themselves will do something wonderful. Did I get you?
No, well, you made me think. Well, so for me personally, I'm PI on another project where we've, our aim is to build a complete software stack, but for science, right? For DOE science. So, we've had this discussion as, all of us together as scientists, and I think I just see basically a parallel in general, but then, you put economic questions, and I think that's when I'm lost. But I guess I see some similarities in terms of kind of thinking about problems and building up the whole a structure to solve the problem.
Yeah, so there's definitely economic impacts to whatever it is that you're doing. There's no discount in there. The tools that wind up get sent over to DOE. I've seen this happen before, where the tools that are initially made for the government or any other perspectives from that perspective, from any other government standpoint, eventually trickles down and is made available. And so I would say the economic impact of everything that you're doing right now is tremendous.
All right, great. Then I'm covered for myself. Good. So I believe that David has suggested that we can take a short 5-minute stand-up break for those, and we will start with Chris Monroe's talk in 5 minutes. But as that's come up, there is a question now. So the question is from Daniel Salazar. Coming from a country that currently has no official involvement with quantum computing, how should I and QC students focus their journey?
Tricky one. Relying on the government is definitely a path to accelerating a lot of the things that you're doing. Each government does that. Creating an ecosystem from the ground up. A lot of these startups that you hear right now that are coming up, Quantropy or Sorrow or any one of them, they definitely love the government funds. Don't get me wrong. But they're not only relying on that, they're relying on ventures that are out there, venture capitalists who believe in this. And the number of people who believe that quantum computing is going to make an impact is tremendous. As I mentioned before, the impact is not just the initial $250 million of funding and money that is readily available right now that people are actually spending with these vendors, but it's in the billions that you have different ventures. And I wish I had, wish I'd shown a snippet of that during this talk. But essentially, there's an entire ecosystem that are out there right now that's grown since about 16 years ago or so, when I personally started looking into this for my own self. the amount of investment being put into this one is now roughly from the millions to the billions. And the ecosystem of people who are in here right now have also blown up from a handful of people that are out there right now to hundreds of handfuls of people that are out there right now doing quantum computing. And that's a good way to start making this the impact. Did that help? I hope it helped.
We have a new question in the Q&A.
Yep.
So Graham Jacobson says, I currently work for a startup, QBraid, that makes learning tools for the quantum workforce. We currently teach a lot of the technical basics, but what would you consider to be important to teach in terms of creating business impact? And Daniel says, thanks.
So teaching business impact, the way I would teach business impact is aligning to, you start from the very beginning around which sector it is that you're trying to solve for. Understand the sector enough to know that there's a couple of pain points in those sectors that simply cannot be solved in current state, right? In terms of the pharmaceutical industries, it's around discovering new drugs or accelerating the delivery of some of these drugs. In the case of some healthcare professionals or health-related items, companies, it's about understanding, like say for instance, you have an MRI machine or a CT scan or something, understanding these images, like deriving value out of what these businesses wind up using is probably where I would start. There's the strategy story of where you start with that and asking the relevant questions, all the way down to what are some of those metrics, the value tree, I would say, of what makes that important to the individual, I would say, the relevant business and technical objectives for those strategic categories. Then you kind of clump that into some relevant problems that you can do that creates a potential impact. So just as to give you an example, right? In drug discovery, typically, you have target identification, lead discovery, lead optimization, preclinical development, and clinical development, roughly. And each one of the different categories are to speed up predictive analytics and machine learning and simulations, save on drug design components, conduct high-quality preclinical research, deliver products and consumers faster. So in that, some of the technical objectives could be to drive useful data, eliminate noise, make decision better, create fix optimization models, inferential learnings that you're going to have out of the preclinical studies, for example, and then that you can kind of immediately tie down into like establishing, say, disease linkages, where you have increased size of target candidates in a database. What does that wind up doing? It improves the chances of drug discovery success by potentially 18%. There's a certain research associated. I mean, you go through, these are examples of business outcomes to quantum that you can potentially deliver. And there are some examples like this that we can kind of help curate and teach people. Consulting companies just inherently just want to do this. It's ingrained in my head. There's a lot to it, but I hope that helps as an example.
All right, thanks. So we are now at 1:30. So thank you, Shreyas, again for the wonderful talk and discussion. Chris Monroe, can you please share your screen?
Yes, hello, and good afternoon. Yes, let me get this going.
Aha.
Sorry, I was just, there was a congressional hearing actually on DOE today, and I was asked to comment in a virtual hearing. Okay, let me see. I'm scrambling a little bit here, but
so while Chris sets up, I would remind everybody that the chat is open and a great place to put questions as Chris goes along. Maybe we can even have a discussion amongst ourselves. And then I believe we'll probably have a little bit of time for questions at the end, depending on how things go. All right, so without further ado, Christopher Monroe is going to tell us about quantum computing with atoms. So take it away.
Okay, thank you. And thank you, everybody. Thank you, David and others, Sasha and others in the Purdue Center for having me here. Look forward to the panel tomorrow as well. And sorry I missed the last couple of hours, but ready to go. So the topic is quantum computing once again, and I'm going to speak on this topic from more of a hardware angle, but even though I'm a trained physicist, have been for many decades, I find myself moving away from physics to a little bit more of a quantum systems engineering perspective. So I want to talk kind of from both high and low levels about quantum computing, and to me, that's what makes it interesting. It's a conglomeration of so many different areas, and if there's one point to take home, it's left physics. Quantum computing is no longer physics only. So with atoms, as we know, any computer worth its salt needs to be used by a third party, and that third party can't need to know what's inside. You want to be able to have a computer that people can pay attention to more on the algorithm side and so forth. So there are interesting technologies out there, as you know, that have been put forth as possible quantum computing technologies. And it's such an early state in the game that, yeah, there's a lot of physics behind the development of good qubits. I would say the two on the left here, superconductors and trapped ions, are really the only two that have been built into systems, built into capable systems that indeed can be used by somebody that knows nothing about atomic physics or superconductivity. Now, I sort of divide some of these platforms into the natural quantum platforms, atoms, photons, and the synthetic quantum platforms, generally in solid state, where we're trying to purify maybe a defect in some type of a solid, or maybe a naturally existing quantum degree of freedom that can behave as a qubit. I think the calling card for that is the interest in topological qubits, which I would say still is firmly entrenched in condensed matter physics. It's beautiful physics, though. The idea that there could be a sort of self-error correcting qubit in nature. Maybe we have to build it. Probably we have to build it. But it's beautiful and deep physics. So yeah, not everything is left physics, but physics will continue to play a role at the bottom. So this next slide is a little bit maybe controversial, but with explanations, I can maybe get through it. Every one of these points has a reference to go with it. And what am I plotting here? This is the error on a single entangling gate over the last couple of decades. I'll talk a little more about what gates are and so forth in a circuit. But as you know, in a quantum computer, you need the gates to be really, really damn good. 95% fidelity doesn't cut it, because if you have a 95% fidelity system, you can only do about 20 things before it's all noise. So the lower the error, the higher the fidelity, the larger the program you can run, and therefore you have a license to get more qubits. So you have to improve the error as you scale. It's a very tricky thing to do. These points are I think the big disclaimer here is almost all of these points correspond to demonstrations with exactly 2 qubits and no more. Okay, so clearly it's a little bit of these are physics experiments just showing how things can get entangled and how good the entanglement is. I think these data points point a little more toward the fundamental limits in certain technologies. They have nothing to do with the system development. There's no crosstalk. If you only have 2 qubits, there's no crosstalk between the other idle qubits, for instance. Trapped ions, we had an early start in the 1990s. We were building entangled atomic clocks already in 1993 or 94. And when quantum computing hit, when I was actually at NIST working with Dave Wineland at the time, the whole field fell in our laps because we had one of the few systems that you could control entanglement with. Well, we had an idea that our system was very pure because these atoms have almost no idle errors. It's all about controlling the systems with lasers. And so the fidelity the error has marched down throughout the decades. Superconductors came along and they're pretty strong. There may be signs that they're saturating on their error, but there's nothing fundamentally keeping them, below 3 nines of fidelity. I think there are materials issues. Maybe there's physics again. I think it's interesting in solid state implementations. I think there's a lot of physics that has to be worked out still. And natural quantum systems like atoms and photons, an atom, we don't manufacture an atom. It's made for us. So there's less physics there. It's more about the engineering, how to control them. Doesn't mean it's totally devoid of physics, but it's interesting to me that these two different platforms really are going in, they're needing different disciplines. Neutral atoms are coming on really strong right now. They're very similar to trapped ions. They're not as good because they're neutral. They're hard to hold on to without distorting the inner workings of the atom. With trapped ions, because they're charged, we hold on to them based on their charge, and that in no way disturbs the internal dipole or quadrupole moments that we use to store quantum information, okay? So these individual atoms in my talk are ions. They're atomic ions. This is a picture of exactly 80 atomic ions that are suspended above this chip. This is a silicon-based ion trap that was built at Sandia. It is fabricated at Sandia National Labs. There's nothing quantum about the trap itself. It's all conventional silicon fab. There's gold plating on the top. It's a little exotic. As there's multi-layers, and we have high voltages, high voltage RF, so that's a little exotic too. But there's nothing quantum about the electrodes. Any electrode material will work. It makes sense. There's 100 electrodes here. You can't really see them. It makes sense to use silicon fab just because the tolerances of the submicron accuracies in placing your electrodes is pretty important. So these atoms occupy a space right above this slot here. They're floating about 1/10 of a millimeter above the surface. Left to right here is about 1/2 millimeter. So they're separated by 5 microns or so. They're glowing because we're shining laser light on them, and they're clearly optically resolved. The atoms are actually very cold. They're laser cooled, and they occupy a space. Each atom is about 1,000th the size of these blobs. The blobs are just diffraction limited spots from our optics, okay? So this is our platform. This is the heart of a ion trap quantum computer. And this is a summer school. I want to, as much as I can, get in a little bit of depth, but I'd like to talk about the system as a whole as well. So I'm not going to be able to go in as much depth as I'd like. So each atom hosts a qubit, a quantum bit. And when we look at the atomic physics, a couple of atomic physics slides here, the atom we're using is ytterbium, 171 isotope of ytterbium. It's a very simple atom when you ionize it once. It has only one valence electron, and it's in an S state, so it's very much like hydrogen. It's even more like hydrogen in the sense that the nuclear spin of this isotope is 1/2. So when you see 171 ytterbium ions, you should think of just a heavy hydrogen atom. The energy splitting that we use to define our qubit is the hyperfine splitting between the 10 and 00 states. These states are not shifted with magnetic field. They're called clock states for that reason. When you make an atomic clock, you have to use states like this. In fact, these two levels are the basis for a very good microwave atomic clock at 12.6 gigahertz. Of course, I spelled out the frequency to many digits. I could probably add more. And when you put multiple atoms next to each other, they have exactly the same clock frequency. So there is no heterogeneity in our qubits. They're exactly the same. We don't worry about that. And I put this in quotes, but when the atoms are left idle and there's a good enough vacuum, and you've done your ion trap physics right, there is no T1, there is no T2. They're both infinite. These states are, well, all right, the excited state lifetime is about 10,000 years, but who's counting? And the coherence time is as long as you want. It's an atomic clock. It's a frequency standard. So the qubit's very good place to start. I sometimes label it as spin up and spin down. You can call it 1 and 0 if you want. Now, to detect the qubit in atomic systems, we use state-dependent fluorescence. And a good atom has a very simple electronic level structure such that you can have a cycling transition on one of the qubit states when laser is applied. This laser for ytterbium is in the near UV. And again, I didn't write the other 6 digits of the wavelength, but we know it very accurately, and we have to tune our laser there. That's not really hard. And the point here is that only one of the states will fluoresce and give rise to the pictures like I showed earlier on the CCD camera. And remember, this line, well, I didn't tell you, this line is 20 megahertz wide. What you remember is that the frequency splitting is 12,642 megahertz. So when you shine that same light on an atom that's in the other state, it's dark. It's way far away from resonance, so it doesn't fluoresce. And this is real data here on the right for a single atom that was either prepared in the bright state, sometimes we call it the bright state here, or the dark state, spin down or zero. And this is obviously an average of many runs, so you can see the distribution. We collect roughly 1 photon every microsecond. We don't collect all the photons. We don't have to. We get to repeat it. It's a cycling transition. And then pretty much the mean of much less than 1 photon if you're in the other state. And so even in a single shot, you can get very high detection efficiency, much higher than you need, okay? So if you had 99.9 detection, you're all set to go with several hundred qubits, okay? If you need several thousand qubits, you might need another 9 there. And actually, we know how to get that, but it's good enough. Now, the more interesting interaction is also with laser light. This allows us to do gates. It allows us to make qubit superpositions and so forth. We use 2 lasers for this, and their beat note is stabilized to match or be near this hyperfine splitting. This is a simulated Raman transition, the same type of excitation you use in solids, Raman spectroscopy. And there's sidebands and all that stuff. I'll talk about that too. If you're wondering why we use ytterbium, here's why. It's because the best wavelength to do this coherent interaction is at 355. That's just the atomic physics. And 355, of course, is a commodity. Getting laser light, even high power at this wavelength, it's easy. It's not incredibly cheap, but the laser has been industrialized. So this is the one we use. It's a coherent paladin. It does cost some money, but it'll last for a few years. And the only adjustment is the knob, turning it on. Turn it on. That's it. So again, I've spent a lot of my life inside lasers, and I'm glad to say that with this, at least with this laser, we don't have to deal with it. It produces a frequency comb, and I won't get into the details. We basically can use coherent superpositions of all the comb separations to drive a coherent transition. Okay, and very, very quickly, the physics that's going on here is we're very far from resonance, so that the simulated the coherent Rabi frequency, it's a 2-photon process, so G1, G2 over the detuning in perturbation theory, if you want. That's the rate at which we're doing coherent stuff, and the rate at which we're doing bad stuff, like off-resonantly scattering from the P state, can be much smaller than the rate at which we're doing good stuff because we're so far detuned, 33 terahertz detuned from a 20 megahertz line. So you get huge suppression. So this laser doesn't measure the qubit, it coherently allows us to manipulate it. So here's how it goes. And if you want to do a gate, if you want to entangle trapped ions in a trapped ion quantum computer, you have a string of ions like this. This is a picture of, I don't know, about 15 or 20 ions. If you want to entangle, say, this one here and this one over here, you simply shine lasers on those 2. It's pretty advanced optics. You have to focus individual beams to hit them. And the important point is that this laser applies a force, and the force depends on the state of the qubit. Okay, and we can do this with selection rules in the atomic physics. It's basically a dipole force. If you know what optical tweezers are, it's very similar to that. Only here, the optical tweezer is red detuned for one state and blue detuned for the other state. So it's either a push or a pull force. And so now you can put it all together. How do we entangle these 2 qubits? Well, we apply this state-dependent force, and what happens is we're modulating the Coulomb interaction, the repulsion. If both atoms are in the same state, they move up together or they move down together, and their relative Coulomb interaction is unchanged. But if they're in different states, one goes up, one goes down, or the other way around, they're a little bit further apart. They're a tiny bit further apart, and so there's an energy shift in that configuration that goes like a dipole-dipole coupling. And that stands to reason because, in a sense, in this regime, you're sort of making a little dipole. You're taking a charge and making it sort of spread out over space. It has a dipole moment. This is a huge dipole moment. It's engineered by the laser, so it's under our control. And that displacement is very small compared to this separation. It's nanometers instead of microns. So there's no the non-linearities are pretty small. Okay, so now we have all the ingredients. I've swept a few things under the rug, and I'll comment on those here. But if you look at the 4 possible states of those 2 qubits, you can see what happens. Remember, down, down, and up, up have nothing going on because they have the same Coulomb energy. But the other 2 states suffer the same phase lag because of their energy. And it's important to note that this goes like the square of delta. So there's no sign. It's the same sign here. This is a nonlinear operation between 2 bits because the product of what happens to up, down and down, up is not the same as what happens to up, up. Okay. So it's nonlinear. And when that phase is set to pi/2, you can use this for entanglement. You can make a controlled NOT gate out of this. So it's that simple. Okay. So the 2 things that I kind of hushed under the rug, one is that this force is not in the Z basis. In other words, the spin is not in the Z basis, it's in the X basis. Remember, in the Bloch sphere, spin down X is up plus down Z, spin up X is up minus down Z, something like that. And so it turns out that our native interaction, we call it an icing interaction, an icing gate, and it's an XX coupling. So our native entangling operation is not a C0 gate, it's an icing gate. They're not incredibly fast. These are tens to even 100 or so microseconds. And their fidelities are in general very high, always limited by the laser though, not by the idle atom. Okay, so this is physics research really about codified 20 years ago. Serac and Zoller, Molmer and Sorensen, you may have heard those names. Now, the other thing I swept under the rug is what happens to the other atoms. This is like a bunch of pendulums connected by springs. If I poke 2 of them, they're all going to know. And that's certainly true. So this is where classical control comes into play. So this slide, sorry, I apologize for math. I guess it's just to prove that I can write math down. I don't just turn knobs. But the Hamiltonian here, when we couple, say, just a couple of ions, the Hamiltonian, when we apply a state-dependent force on a single ion, I, is given by a sum over all the normal modes. The oscillating modes of these coupled pendulums, they're all tightly coupled. They all have normal mode frequencies, and we're coupling to all of them. And there's the force might be off resonance from all of them. So we have to take that into account. So we have a spin-dependent force. There's the spin dependence, is sigma x, and the force is just A plus A dagger, the position operator of the mth normal mode. And this is parameterized by something called the Lambdicki parameter between I and mode M. It has the wavelength of light in there because that's the force is coming from an optical tweezer effect and the length scale is a wavelength and so forth. And when you evolve this Hamiltonian, basically exponentiate it, something kind of miraculous happens. Usually if you have a Hamiltonian with non-commuting operators, you have an infinite series in the Magnus expansion. But this infinite series collapses to just 2 terms because A commuted with A dagger is a C number, and therefore it commutes with all higher order powers. Okay, so you can get rid of this 3rd term, and you're left with basically what you have down here. That what I told you before, you get this icing interaction, but you also get this type of a spin-dependent force. And I'm not sure I didn't write down the chi operator here. Sorry about that. This has A's and A daggers. It creates phonons. All right, not a surprise. I told you we're poking 2 atoms. We want to entangle their qubits, but we're left with all this motion that's entangled with the qubits. That's bad. And so here's where classical control comes in. We have all these normal modes and they're driven off resonance. And of course, a harmonic oscillator, when you drive off resonance in phase space, they undergo circles. But these circles all have different frequencies, and and you're driving circles in 2 directions because remember, spin up goes one direction, spin down goes the other. So what happens is the phase spaces don't close, and you're left with entanglement with phonons. And when you trace over the phonons, if you want a pure qubit state, that's decoherence. So you have to close all the phase spaces. So it turns out by simply designing our laser pulse in this way, it's just a simple AM. We divide it up, looks like into 9 segments, and we optimize the amplitude of these 9 segments, the relative amplitude, so that all the phase spaces close. So they're no longer circles; they're sort of piecewise circles, but they have different centers of curvature, I guess. And we can engineer the laser pulse so that all the phase space is closed. Okay, so we can operate a gate on any pair, and that's how we do it. We pre-calculate the laser pulse shape we need for every pair. That sounds expensive, but it's classical expensive. We're okay with that. Classical computing is great. So we can use their classical computers to sort of design these pulses ahead of time. We have to calibrate them. If the ions drift a little bit, we have to recalibrate all this stuff. So there's a lot of classical overhead here. Okay, so the next slide is the cute animation of how we execute a circuit in the trapped ion system. So the first thing we do, so here's a circuit up here, time, space. Here we have space vertically, 7 qubits I've drawn on the circuit, and left to right is time. We first initialize all the atoms with optical pumping. That's kind of boring. And then we run these gates, and you'll notice that the entangling gates, you can see the ions are animated here as having feeling of force. When we have a single qubit gate, like right here, nothing happens, just a spin flip. Those are pretty easy to do, and so forth. So this is how you execute a gate. You have to pre-design the laser pulses to do what you want. And then after your circuit is executed, you measure them. Again, similar to optical pumping, we send another laser, and the atoms that are glowing are ones. The atoms that are dark are zeros. Now, one thing I didn't note is that two things, and these are architectural niceties in this platform. One is that we have all connectivity. We can do a gate directly between any pair, no matter where they are in the chain. We're not going to do this with 10 million qubits in a single chain. I'll talk about that later. But with maybe 50 or so, this is entirely possible, and it's been done. The other thing I want to mention is that these gates, the wiring between qubits is flexible. It's reconfigurable. There are no wires. We turn our laser beams on and off. It's all classical control. So here's sort of the guts of what a real system would look like. And we use a kind of a weirdo parallel acoustoptic modulator that controls 32 beams. We have full amplitude, frequency, and phase control of 32 individual beams. We align them on 32 ions in a trap. That is tricky. We have to line up the ions and the laser beams, make the ions equally separated. There's a little bit that goes into that as well. But it becomes an RF control problem. So we have FPGAs and RF system on chips that drive 32 channels of 200 megahertz stuff to execute our quantum computation, and that's it. Well, that's it. When we built the precursor to this system with only 5 qubits, actually, we started recognizing that we were not doing atomic physics in the afternoon. We were tweaking all the laser beams, and in the afternoon, we were running algorithms. But you can see in between running algorithms and tweaking laser beams, there's lots of stuff. Remember the laser pulse shaping. We have to calculate these and calibrate them all the time. But then there's an interesting layer of this stack that I'll call the computer science part that compiles a textbook gate or some algorithm you might find in Nielsen and Schwang into our icing XX gates, okay? And that compiling step is really important. It allows you to save lots of time and efficiency in running things, okay? So here's the bad news, of course. If you looked at my lab 5 or 6 years ago, they would look like this, a typical atomic physics lab, which is just a mess. I mean, way too many wires, way too many knobs on way too many mirrors. But this is an experiment. It's a physics experiment. We want flexibility so that we can do different types of science on a single device. But over the last few years, we've, with not too much exaggeration, we've condensed everything you see here into this box. The students are not inside the box. They're actually, they can run from their office or from home. And this has been great over the last year. This box has everything we need, including in the box is a Sandia chip that's in a vacuum chamber, and all the lasers and optics to run circuits are inside that. Now, this is research that is pushing the boundaries of what you can do at a university. It's not cheap to build something like this. We have many commercial industrial collaborators, and it's funded by IARPA and the NSF STACK program that realize that to build a research quantum computer, you have to do more than just physics. And so I mentioned Sandia already, but these other companies that do optical development, we've integrated some of their products. Coherent makes the 355 laser I showed. L3Harris makes this multi-channel AOM for lithography, actually. And we work very closely with that group to retask their device which is highly engineered. It's a beautiful device to use it to hit atoms instead of upper levels of a CMOS chip. Okay. AOSense and Cold Quanta works on miniature vacuum systems, and AOSense makes the tunable lasers. So when I talk about a full stack quantum computer, we noticed that not only were we running algorithms in the afternoon, we were getting lots of interest from people across the world who wanted to run algorithms or quantum simulations, even on small systems with only 5 qubits or something. And so since about 2014 or so, we've been forming lots and lots of collaborations with computer scientists, researchers, non-atomic physicists, or physicists that are not atomic physicists, put it that way, to do all kinds of different aspects. 2020 was a very busy year. And I want to acknowledge my colleagues. When I was at Maryland, they were key postdocs in the group. 3 of them are now on the faculty at Duke, along with me, and Guido went to Rice, and they're all building their own ion trap systems. I want to give an example of a couple of these applications. One of them that's my favorite actually touches on condensed matter physics, magnetism, and another one touches on cosmology. So very, very briefly, this is from a few years ago. It's a quantum simulation where we apply this Hamiltonian. It's an all-to-all icing interaction. So they're not gates, they're not discrete gates, like I said, but the physics is the same. We illuminate the entire chain of ions with a big fat laser beam, and all of them feel that force at the same time. So you end up with a simultaneous icing interaction between all pairs, and notably the interaction falls off with distance. And we can control how it falls off with this power law. Alpha is the exponent, and it can vary between 0 and 3. We typically tune it to be around 1 or 1.5. But this is an all-to-all icing interaction, and we can apply an effective transverse magnetic field. Now, what's interesting about this Hamiltonian, of course, is that it emits a phase transition at 0 temperature. It's driven by quantum fluctuations, if you want. These two terms are not commuting. It's a very fundamental Hamiltonian. Here, we're interested in a different type of a phase transition that is not an equilibrium phase transition. It's a quench experiment, and it happens even at infinite temperature. Okay, so we have a finite system. So infinite temperature means you have equal population at all the levels, I guess. And so in this experiment, we prepare the spins all along the x direction. We turn on this Hamiltonian, and then we measure along x. It's a very simple experiment, actually. And what we vary is B and J. Is B large or is J large? Well, if B is really large, what happens is all of the spins precess around the z-axis. And so if we measure along x, we're going to see oscillations. Just plain paramagnetic oscillations, if you want. If J is really big instead of B, then the spins will order along x. Of course, they started along x, so there's not much is going to happen. But the competition between B and J is very interesting. So if we measure the total magnetization, that is, just measure the brightness of all the ions, that would be this variable here. As we increase B over J, we see, well, when B is very small, nothing much happens. There's a little bit of dynamics here. As I said, they're already ordered along x. But when B is much larger, we see those oscillations I talked about. They get damped out because of inhomogeneities and so forth. Well, they all have a slightly different frequency, and you end up getting dephasing. But this is quite different dynamics. And if you go in the middle, you see something kind of halfway in the middle. I wouldn't exactly call that a phase transition. So we measured something else, which is the average two-body correlator between all spins. Remember, in a single shot, we get to measure every single spin with very high efficiency. So we can form any correlation function you want. Here's a two-body correlator averaged over all pairs. And now we're measuring this correlator as a function of the number of spins, as a function of B over J for different numbers of spins. Yeah. And you expect to see a dip at some intermediate value. The dip is supposed to get really sharp, and it never really got that sharp. There's a logarithmic divergence in the thermodynamic limit when you have infinitely many spins. And so it does kind of get sharper. By the way, these dashed lines, the bad theory, this is mean field theory. So there's stuff going on beyond mean field, which is not a surprise. There's a lot of entanglement here. Well, okay, so that was interesting, but we measured another correlation function. This is an n-body correlator. we measured a weird order parameter, and that is what's the size of the largest domain in a single shot. So we have to make a single shot measurement of all the spins, and we just record the largest domain. And we plot that as a function of B over J, and we indeed see a much stronger kink. Well, yeah, it's a matter of taste, whether you want to call that a phase transition, whatever you want to call it. But the position of that kink, we could not calculate otherwise. It looks like it's right around 1. It's actually less than 1, a little bit. We couldn't calculate it. It's 53 spins, and the Hilbert space is too big. So this is an example of a problem we couldn't solve. So that's sort of where quantum simulators are going. We've been collaborating with lots of theorists around the country and the world in many different aspects, including making time crystals, which is an interesting topic. It's into its own right. But in general, non-equilibrium quantum physics is really an excellent. This is a great test bed for that type of physics. So I want to start to move a little quicker. One of the other applications that's been kind of fun is something called scrambling, testing whether a unitary process scrambles or not. So scrambling is more than entanglement. It's, in a sense, the entanglement at all depths, at all levels. If you want to think, it's not exactly diffusion because it's coherent. It's a unitary process, but it's sort of like that. And the relevance to black holes, I'm told, is that black holes, if they're described by a unitary quantum process, are probably the fastest scramblers that we know of. If you put a qubit in a black hole, it gets eaten up by the entire system very quickly, I guess. And so we basically implemented this very simple 7-qubit circuit. And the whole point here is to test whether a unitary that we implement, does it scramble or not? That's a property of a unitary process, and you need at least 3 qubits for that. 2 qubits, scrambling and entanglement are exactly the same thing. There's no difference. But with 3 or more qubits, you can have states that are entangled but not scrambled. Of course, if they're scrambled, they're entangled. So it's sort of a superset, if you want. Entanglement's a superset of scrambling. So here's the circuit. We basically prepare an unknown, or well, it's known, but it's a random qubit state here. All the others are zeroed. And we form entanglement across these pairs as noted. We implement the unitary, which is itself some circuit, and we actually can tune the amount of scrambling. It's only 3 qubits, so we sort of understand what's going on there. We also implement its inverse. So this measurement of scrambling is related to something called an out-of-time order correlator. You've heard of that, OTOC, where you evolve a system forward in time and backward in time and make a correlator. So you can sort of see that happening in this circuit. So conditioned upon a Bell measurement in any one of these 3 pairs, what happens is the unitary scrambles if and only if the state gets teleported from bit 1 to bit 7. So we can simply test different input states and see, did it make it to the output, and change U. And so this is basically a litmus test for scrambling. And to me, what's kind of amazing is that there's this connection between scramblers and black holes. So I won't call this a black hole and its inverse, but that's sort of at a tiny scale what it's modeling. But Lenny Susskind at Stanford and other theorists, they tell me that entanglement is deeply related to what happens when you go through a wormhole. Anyway, I'll leave that there. But here's a picture of a real wormhole and 2 black holes and going through there. So there's this deep connection between quantum information and cosmology, which is just fascinating. Anyway, I'm on thin ice already there. But I'm going to maybe skip a little bit here since I'm running a little low on time. I want to talk more about systems now and how we scale. I hinted earlier that we're not going to put 1 million ions in a single chain. Or if we do, we're going to have to deal with the consequences, all kinds of modes of motion and so forth. But there is a way to scale by moving the atoms in front of a head of sort of like a tape in a head. The atoms are the tape, and the head are laser beams. You can imagine putting lots of atoms and linearly moving them. This is like a real Turing machine. You're moving a tape across a head. And of course, this has limited connectivity. There's only 4 laser beams. So you can only do gates between sort of nearest neighbors and next nearest neighbors. You can add more laser beams, but we don't want 1 million laser beams, that's for sure. Okay. So, the idea of shuttling ions around to scale up is an interesting one that dates back to almost 20 years ago. Dave Wineland and I were thinking about how to do this in the context of a very complicated ion trap where you have lots of electrodes and there's modules. You know, you might do an entangling gate with just 2. That's very clean, no crosstalk. And then when you're done, you can rip out this atom and have it fly onto another module, okay? Lots of engineering you need to do here. You probably need multiple species of atoms because you need to do sympathetic cooling. When you pull an ion from its neighbor, they get very hot, and you have to bring them back to being still without using laser cooling. So by doing sympathetic cooling, you can keep your qubits cold while having sacrificial sort of refrigerator ions in the background. We think this shuttling idea will get to several hundred qubits, but beyond that, we have even more plans, and this will involve photonics. Obviously, trapped ion qubits are optically active. We use optics to control them. We use resonant optics to measure them. You can actually map a qubit from the atom to a photon. Polarization or color or time delay, the usual tricks. And the idea here in this high-level architecture is to get a bunch of modules of maybe 50 or 100 ions each. Maybe you're doing shuttling in here to get to several hundred. But at a high level, you can map information through fibers. And if you have an unblocking optical switch, an N-by-N optical switch, and you can herald the entanglement based on some high-efficiency detector over here, depending on the configuration of that switch, you can entangle this ion with that ion, this ion with that ion, all in parallel. So this is obviously a concept right now. It's a high-level architecture. And what's neat about this architecture is it's fully connected, even to scale. You can connect any pair. And so it sort of harks to the multi-core architecture we think of in CPUs. I wanted to, this is summer school, and I feel I should probably give 2 or 3 more lectures, I suppose. But the way this interface works is pretty simple. And it can be done with low errors because the emitters are exactly the same. These are atoms. The wavelength of light that is emitted is exactly the same between these atoms. Basically, we do a Hong-Ou-Mandel interference on a 50-50 beam splitter, and depending on the coincidence event we collect, these atoms can be entangled. And this is a sort of known protocol. It's been developed in many platforms. And the state of the art, if you ask, why aren't we doing this today? Well, it's slow. It's slow because we're not very good at collecting this light. It's not very efficient. It's a p-squared experiment. You know, if it's 1% for each ion, then it's 10 to the minus 4 to get 2 photons to interfere. So that's why the p-squared goes in the rate here. And the state of the art right now is almost 200 per second. I hesitate to say hertz because it's not synchronous. It's sort of random times. You can make it synchronous with a first in, first out kind of architecture and a buffer. But we believe we can get to maybe 10 to the 4 per second. And this still might seem slow to connect photonically, but the good news is the qubits last forever. The idle qubits last forever, so we have time. Hopefully the algorithm is not too deep. So as I mentioned, you can think about making a data center type object with a bunch of these modules. This is really starting to look like engineering. What I like about it is that these modules are stamped out. They're all identical. If we can sort of get a manufacturing process going, then this is really, as far as I know, the only feasible architecture to scale for any quantum computer. It has to be modular. I think anything complex has to be modular, and this is how we're going to do it. Now, I showed you the picture of the lab, which is horrible. How do you scale that? Well, we've already made some work on that, bringing it down to the meter scale. But Jungsang Kim, my colleague at Duke, and also co-founder of IonQ, our startup company, he's miniaturized things. And with cold quanta, we've figured out a process to make the whole vacuum chamber fit on the chip itself. At MIT Lincoln Labs, they're doing even better. They're integrating a lot of the optics on the ion trap chip in vacuum. So that's something we look forward to in the future. So what I want to springboard to in the last few minutes is that, yes, indeed, this looks like an industrial endeavor. And so IonQ is a company that was formed just a few years ago. We've built several generations of quantum computers along the lines that we've done at the university. We've just made it more autonomous, better behaved. The engineering is just better because we have engineering. Now, IonQ has been a private company, but we're actually slated to become public very soon, probably within a month. Everything's all set to go. and it'll be a $2 billion market cap for that company. And so we now finally have the resources to really try to execute this goal of scaling up in a modular way. Now, we obviously need a big user base, a user community, and we've worked with our partners at AWS and Microsoft Azure to get our systems on their cloud services. We're also in the works with IBM to do something similar to that. IBM Qiskit is already being developed to support the native expression, our XX gates, for instance. You can find that on their software tools. So it's a very fun time in industry as well. You'd think industry would be everybody's beating up each other. No, it's actually, you know, we're all kind of relying on each other. So it's actually a wonderful community. Of course, I would say that in public. No, it's really true. So to give you an idea of the automation at IonQ, this is loading exactly 24 qubits in this chip. This is a micrograph of the Sandia chip close up. We actually load from a zone over here, one at a time. And you can see here in real time, they're being captured in the computer zone, and they're even zigzagged. When we get up to 24, we straighten out the zigzag, they occupy their positions, and we refocus the laser. This is all done autonomously. And now we're set to go for a long time. This crystal probably lasts several hours. If we cool the chip to 4 Kelvin, it'll last for months. It's all about vacuum. And we do have some systems that are cooled to 4 Kelvin. We don't need to go to millikelvin temperatures, though. We only go to low temperature to get better pressure. You know, I think I'm gonna, since I am running out of time, I want to leave some time for questions. So IonQ has been running many benchmark applications. They've been spending particular efforts on running variational quantum eigensolvers like everybody else, I guess. But the one thing I'll note is that this compiler step is really interesting. In a variational algorithm, you typically find this little subcircuit where you do a tiny rotation. You know, you're testing the landscape. You want to make a little bit of you want to make a tiny move, and you surround it by C0 gates. Now, for us, C0 gates are as expressive as a full XX gate. They're expensive, but if you do an XX gate for a tiny angle, it's much cheaper. And it turns out this gate takes 2 C0s. If you look at this circuit here, it's the same circuit. We have cheap rotations. They're single qubit operations. They're clean and fast. And then we have a very small entangling operation. So this is much better for us than that. Much cheaper, much higher performance. And similarly, when you get higher level circuits, you can compile them as well. This allows us to compress the number of gates we need to do something by orders of magnitude, not just one, sometimes 2 orders of magnitude. So, you know, we have lots of research involved in that direction. So I'm gonna stop and just kind of wind down and note that you know, I sort of wear both hats at a university and a company. We're developing the same tech. You know, at the university, we're doing it for science. In industry, we obviously need to have commercial partners. We need to sell things eventually, or at least have a path to that. And I like to think that these 2 corners of the community are a little bit complementary. That's changing fast. Universities, you know, quantum physics is in our blood. We're comfortable with it and so forth, but we typically don't build things at a university. That's changing. It's getting easier to do that. Industry may not have been as familiar with quantum as universities, but they build things. So that's the complementarity, but that's changing as well. They still build things, they always will, but we're getting a quantum workforce to play in industry. And I think a lot of the speakers for the summer school, of course, are coming from industry, which is great. And I'm sure that's a mission for the Quantum Center at Purdue to be able to bridge that gap between university and industry. And of course, government labs are going to play a critical role in that translation, where they sort of have everything. I think the one thing they're missing, and that they're quickly picking up on it, is that they haven't, you know, the national labs outside of NIST really haven't performed in this space for more than a few years. But things are obviously changing really fast right now, especially at the DOE labs, places like Oak Ridge. So my last slide here, a little bit of an ad for what we're standing up at Duke. We're standing up the Duke Quantum Center. It is a user facility that will develop the highest class quantum computers, but for science in ways that companies probably won't do, certainly in the long run. And this co-design process, understanding how QCD works in nuclear physics and implement that in a quantum computer is something we're very interested in. It can inform how we build the next generation systems. And with that, so many colleagues, you might recognize Robert Calderbank, one of the co-inventors of quantum error correction, Ken Brown, Jung-Sang Kim in particular, and the others are actually very young faculty that are moving over there. Natalie Clow comes from Caltech via Washington. She's a nuclear computational theorist who's very interested in using quantum computers to do the next generation compute in that space. So this is a very old picture. I apologize that for those of us at IonQ. We're up to about 75 employees right now, and my group, formerly at the University of Maryland, we're now firmly entrenched at Duke University, and there we are in our former home city with all the support from those inside the Beltway and the agencies. Thanks for your attention.
All right, thank you, Chris. Thank you for the very nice talk. So we have a lot of questions. Maybe we can try to go through a few of them really quickly. Zain Kareem asks, do you know what the major factor that caused the improvement on the error curves over the years? Very early in your talk. Just technology? I think you said that it was, they were all
that's
single or
interesting.
2 qubit experiments, right?
So I can certainly speak on the trapped ion space. I was here for pretty much almost all of these points. I mean, when we started, this was 1997 or something. Nobody had really controlled a single quantum gate at all. I tell my students sometimes that at the frontiers of science, your data should look horrible. That sounds kind of funny sometimes, but if the data looks too clean, you didn't push the system enough. You should have a signal to noise of 1 or 2. So when we were doing these early experiments, we were pushing them to the limits. That there was literally duct tape and glue holding the optics together, things like this. And so I would say maybe the answer to your question, I have another slide that showed it. The answer to your question in the early stages is this. You're not going to get super high performance with a system that looks like this. So in the early stages, the point of doing that research was not to get high fidelity, but just to show how it might work. We knew at that time that the limits of fidelity were going to be way down here, 10 to the minus 4, 10 to the minus 5, or something like that. We knew that. We also knew that our laser was moving around in the breeze, literally. Air currents were very important, any vibrations, things like this. So all of our air budget were things that we sort of understood. And that's really what we were chipping away at. That's the story with trapped ions. Understanding what limits you and fixing it, inventing technology to fix it, because it's not quantum physics. It's vibrations, it's lasers. These other technology, neutral atoms are very similar, I think, kind of like ions.
Hey, Chris, can I actually lead into that one with another set of questions from the chat?
Yeah.
One question is, how many qubits would be in one ion trap module? And the second question is, currently the neutral atoms could reach around 200 qubits, although there's less control of individual qubits. So I would like to hear kind of how you think those two compare and fit into the modularity science.
Yeah, finishing quickly. I mean, I think there are a lot of other talks on superconducting technology. I think the early experiments were just, again, nobody's made circuits out of superconductors in that way. And they came up with some physics issues in the materials. I'd say, IBM and Google and the groups at Yale were really leading the charge there, understanding the limits and getting different geometries. So I won't comment much on that. But to the second question, so how many do we think we can put in one module? I think the number is probably between 30 and 200. Now, when you get to 200 ions in a single crystal, you're worried about all those normal modes, and there's tightly spaced. It's a forest. Well, when you get to 100 or 200 ions, it turns out that you can deal with local modes if you go a little faster, a little higher power in the laser, and you can just deal with local modes and close local phase spaces. It becomes easier. So that's certainly a possibility.
I see. That's cool.
But ion traps, there are other ion trap systems that have dealt with several hundred ions. Just like the neutrals, they have less control. These are penning traps, a 2-dimensional disk that rotates, and you can address into individual ions there. So yeah, trap dines have always been about individual quantum bit control to execute the gate-based model. Neutral atoms are way behind in doing a gate-based model quantum computers, so they're rightfully using their system, deploying it for these quantum simulations, more like what I showed in that magnetism example. But they're coming along strong. I think the one fundamental difference is that they're probably going to have a higher fundamental barrier than we do in trapped ions. It's because to trap neutral atoms, you have to distort the qubit just to hold on to it. And the traps are very shallow. The vacuum is much more difficult to deal with to scale. So yeah, I think it remains to be seen exactly what tech gets invented in neutrals to catch up with trapped ions. What's interesting to me is that they use the same controllers though, optical controllers. So I love the neutral atom community working on optical tweezers, and I hang out with them a lot and look forward to working with them on inventing better optical control technology.
Great. One more from the chat. Let's see here. In your opinion, so the question is, could the different quantum memory layers be hosted at different sites? Also, what is your opinion in scaling with repeaters versus optical fibers? Yeah, so how does optical and ions play together in a network scale?
Right. So, I mean, I showed concept pictures of how we're going to scale, of course, and they do involve optical interconnects. But, you know, for us, we don't worry about, you know, huge distances here. Let me go to this slide here. You know, they only need to be local with a few meters of each other. And, you know, everything here is classical. This is a multi-port optical switch. All the fibers are classical. They just happen to be piping single photons. What's quantum is this interface, just getting that single photon into the fiber. So even if the photons are UV, you know, the marginal loss in fiber, fused silica fiber of UV is still only, I don't know, 1/10 of a dB per meter. So it's not so bad. You're not going to go 10 kilometers with UV. You need to go to an ion like barium that has green light, that has visible light, and you can even convert single photons up to telecom. Then you can go large distances. So in the long run, yeah, you can distribute your computer among sites, maybe not between New York and California, but in quantum computing, I don't think there's any need to do that right now. And the second question had to do quantum repeaters versus optical fibers. Let's see, a quantum repeater, the concept, I guess it implies that you're using optical photons. I suppose you could use microwave photons, but then your fiber is a couple of feet wide and it's at 20 millikelvin. So optical fibers and quantum repeaters are sort of the same thing. The quantum repeater, you're going to need long distance, so you're going to want telecom. But the other important component of a repeater is having a local quantum computer at the station that allows you to, in a sense, amplify. Shouldn't say that word, but it allows you to purify the quantum state and get it on its way. So you need to have a very adept quantum computer at the nodes, and they may be individual atoms or ions at those nodes. But the conversion to telecom is really important. And I know there's some materials folks here that work with, you know, optoelectronics. Single photon noiseless conversion from a random wavelength in the visible to telecom is a big need.
Excellent. Agreed. One question about the basics of the physics. So Maolin asked, I think he's referring to the your MS gate, your Isingate.
Yeah.
Can you explain again why it is not in Z basis but X basis?
Oh, it doesn't have to be, but so this is going to get into the atomic physics a little bit. The reason we use the X basis is that there's probably a theorem behind this. If we apply a state-dependent force in the Z basis, that means that we have to apply actually a Stark shift. The laser drives an AC Stark shift that's differential between these two levels. If that happens, that means that these two levels are also magnetically sensitive. So you can't do it with clock states. If we instead stored a qubit here and here, then we could do a ZZ gate, but then we would be sensitive to magnetic field noise. That's the basic reason we use the X basis. But the physics is really, I mean, physics is always independent of basis. But if you want to think of it as a Z dependent force, that's fine. It tells you what the physics is. But the Molmer-Sorensen gate is actually an X dependent force.
All right. We also have question on or a comment on YouTube. Incredibly interesting. Do I understand it correctly that IonQ is already closing the SPAC deal next month?
Don't know.
Come on, Chris.
No, I look seriously. We're the IPO process. I'm definitely not the expert, but there's lots of variables that go into it, and it's not always up to us. Things have to be approved, paperwork has to be filed, but we're hoping it'll be sometime this summer.
Great. All right, so I think we can give Chris another big round of applause virtually. Thank you for pedagogical at times and nice talk to scalability. So let's take a minute or so to refresh before the next talk. Do we have the next speaker? Okay.
I don't see him in here yet, but we'll keep a lookout. Hopefully he'll be joining soon.
Я не могу видео.
I would just take this opportunity. Sorry, I would like to take this opportunity to thank you, Chris, for agreeing to speak at the school. It's really an honor for us to host you as a speaker. Thanks again for joining. Absolutely fantastic talk. Amazing results. Thank you. I wish we would host you in person next time for the next school.
Hello, Blake.
Hello.
Hello. Feel free to share the screen, grab the screen whenever you get the chance.
Okay.
So while that's getting set up, our next speaker is Blake Johnson, whose title is slightly updated from the PDF, which told us it would be an overview of IBM quantum computing hardware and software and Qiskit runtime. But I guess I'll let Blake clarify that and tell us throughout the next hour.
All right,
Thank you.
great. So yeah, I will be telling you about IBM's hardware and software platform, but I want to connect it to a sort of an underlying need that drives our choices that we're making in that development path, which is that we have this desire to make quantum computing frictionless, and that means removing the barriers to finding value or utility out of it. So that in these early sort of research stages, that the research questions you want to ask are easy to express. The system kind of works with you to getting answers to those things. And of course, as we're driving towards actually be able to find applications where you can deliver real quantum advantage, that the system again is sort of working to help accelerate our path towards delivering those applications. Hopefully you've been thinking a lot during this summer school about this question about what we can do with quantum circuits. So I'm not going to dwell on this topic, but just to kind of put our own framing on it, we really think of quantum circuits as being a kind of the fundamental unit of quantum computation. And so, everything we're doing is about sort of delivering quantum circuits with high quality and delivering as many of them as you need for an application of interest, and delivering the kinds of circuits that are necessary to express the algorithms that we want to run. And there's different application domains that people have been thinking a lot about, right? You can start with kind of the original motivation from from Feynman, thinking about using a quantum machine as perhaps being the right way to simulate other quantum mechanical systems. And that has the applications that kind of derive from that we think about in terms of chemistry, simulation, material science, and so on. There's kind of the algebraic problems, right, where a lot of the excitement about quantum computing started in terms of factoring, but of course people are thinking in terms of the same sort of domain for machine learning problems, or again in simulations, but in more mathematical context with differential equations. And then there's the space of search problems, where you have things like sampling problems, optimization, and so on, where I think there's more open-ended questions about whether or not exponential speedups exist in this domain, or merely quadratic ones. And so there's a lot of kind of heuristic activity going on in this space. But I think there's reason to believe, kind of from what we know already from quantum walks and so on, that there must be some kinds of graph problems where you can utilize the concepts of interference and so on to find methods that should scale better on quantum hardware. So these are the kinds of application domains that we at IBM are sort of focusing on in terms of near-term efforts for finding problems with quantum advantage. And the kinds of systems that we're building to enable those explorations are like this prototype quantum system 1 that is in Yorktown, New York. And this particular one from the image here was built a couple years ago, but it's of course not just one system any longer. It's now there's now a large fleet of quantum systems available online, which you can see by going to our online catalog at quantum-computing.ibm.com. And so there's 20 some odd systems online and a number of simulators which have different simulation methods for Clifford circuits, which can be very efficiently computed. Extended stabilizer circuits, which are circuits that are kind of close to Clifford circuits. So they also have sort of a limited number of gates that take you out of the family of computations expressible only with Clifford operations, to also have a few so-called T gates and so on. And then sort of a stabilizer, the Chasm simulator, this one in the bottom right-hand corner tries to sort of automatically pick the best simulation method for the circuit that's provided to it. So if you don't know which simulator to choose, you can start with that one, which of course has to make the most pessimistic assumptions about the size of the circuits you can simulate, that it will automatically choose from among the various methods that are built inside. The number of systems that you see here is larger than the ones that are available through through the open. If you have an unpaid account, there's a smaller number. You can see the kind of little lock icon next to ones that require an elevated level of access. But we have different programs for researchers, academics, and of course, paying customers to get access to the larger fleet of hardware. But so I guess to connect back to the story from the title, what I want to say today is that, you know, as we look at quantum hardware and really quantum systems that we build up around that hardware, we really think of kind of three fundamental ingredients that we need to solve in order to really deliver this frictionless experience of using of quantum computing. And those three ingredients that we think are critical are quality, meaning how large of a circuit can our system deliver with minimal errors. Right, this is kind of maybe the most obvious need of quantum hardware is that you know, if the circuits that you want to express are connected to, you know, actual problem, I can maybe tolerate a few errors. But as soon as I have many more errors, the output of the circuit becomes very quickly indistinguishable from noise. Right, so it is absolutely, you know, critical that we build hardware that can execute circuits faithfully, so that the output actually represents the execution of the ideal circuit. So that's maybe the one that's most familiar and has been talked about the most. But what I guess I would say today is that, you know, we don't think that this it's obviously critical, it's obviously necessary, but it's not sufficient. In the sense that we also need systems that have capacity, meaning they can run many circuits per unit time, because many applications require not just execution of a single circuit, but executing a family of circuits and doing some analysis or post-processing on that collection of outputs. And finally, we also believe it's important to be able to have a large variety of circuits that are executable by your hardware. And in particular, what we think is important here is to exit the domain of static circuits, which are circuits that kind of all the information is known about in advance, in terms of there's no real-time data that's you know, coming out of the quantum hardware that is used to influence the circuit itself. So you don't have things like feedback or feed forward. To exit this domain of static circuits to the domain of dynamic circuits. And we think this has potentially could potentially change the kinds of circuits that we can execute with low errors on near-term hardware. But so let's go through these three different components kind of one at a time. So let's start with quality. So at IBM, we've taken to a metric called quantum volume as a means to measure the quality of a system. Quality is kind of a hard thing to pin down, right? Like these real quantum hardware has many different metrics that are associated with it in terms of the error rates of the fundamental components, whether they're single qubit gates, 2 qubit gates, measurements, there's crosstalk measures and so on. And all those things are important. But if you want to know how well your particular piece of quantum hardware can execute a particular application, it's somehow you need to know how all those different kind of component metrics are going to participate in that final result. And in some ways, these things are they interact in surprising ways. You know, correlated errors end up making it's sometimes hard to sort of factor or compose the actual ingredient errors into a way that you can kind of meaningfully reconstruct the expected performance on a real application. Quantum volume tries to solve this by looking at the performance of quantum hardware on random circuits. And in particular, quantum volume is effectively, from a definitional standpoint, it's the size of the largest random square circuit that your hardware can faithfully execute. We chose square circuits because really we're trying to develop a metric here, right, that can represent arbitrary applications. So we don't want to look at just very narrow circuits that are very deep, or very wide circuits that are very shallow, because we believe that, you know, in general, applications kind of need to flex both sort of space and time. right, which is kind of the width, circuit width, and circuit depth. So we're really we chose, from a metric definition standpoint, to look at square circuits. And then the quantum volume is basically 2 to the power of the size, either the width or the depth of that square circuit. So, there's been a lot of conversation in the last year about this kind of exponential form, right, 2 to the n. And, there's no problem talking about quantum volume just in terms of this effective number of qubits, the exponent. The reason we expressed it this way was to try to give a measure which connected to the kind of the cost of classically simulating such a circuit, right? Because the classical simulation costs also scale exponentially. So this 2 to the n is kind of represents, from an approximate standpoint at least, the kind of equivalent classical cost. But of course, as we get better at delivering hardware with larger and larger quantum volumes, it will make more sense, to refer to kind of the log base 2 of this thing, or really just the kind of the effective number of qubits. So, there's a lot of things that go into determining the quantum volume of a circuit, right? We need, low gate and measurement errors, we need long coherence times. Parallelism is something that goes into this too, right? If you have very good gates, but you can only execute them serially, you can't execute them simultaneously. That leads to circuits with larger effective depths than hardware that can execute gates kind of in full parallelism. If you have larger connectivity, you can execute these random circuits in shorter depths because the kind of the swap networks or permutation networks that you see in random circuits and are much cheaper if you have a richer connectivity graph. And then, like I've talked about before, crosstalk matters a lot too in terms of the composability of the errors. And then you have kind of much more practical things, right? Like this quantum hardware is driven by some kind of classical control system, and the stability of that control, whether it's optical or microwave control, right? The kind of the stability of those clocks and the powers and so on, ultimately limit quantum volume because you need your system to kind of execute at its highest performance throughout the execution of the entire family of circuits. So quantum volume is really an attempt to kind of wrap up all these concepts into a single number. And if you look at how we've been doing in quantum volume over the past few years, we made a commitment or a prediction in some way that we would be able to double this quantum volume. So it's an increase in the exponent by 1 every year. And so far, we've been able to keep that pace or even go a little bit faster, with last year achieving a quantum volume of 64 and then 128 milestones in the same year. And those improvements have largely come from improving the physical error rates. In the next few minutes, I'll talk in some detail about kind of the necessary advances to achieving quantum volume of 64 and 128. But I guess from a forward-looking perspective, we're really looking towards this point that we think of an inflection point where we can transition from improving quality of our systems and the quantum volume of our systems through physical error rate improvement to encoded scaling, right? We can use taking some quantum error correction to effectively trade number of physical resources for numbers of logical resources. And we expect that transition point to really lead to a significant change in slope, effectively in the quantum volume that hardware makers can deliver year on year. So let's these quantum volume of 64 and 128 results were achieved on our most recent families of quantum processors that are available online. We have 2 primary families of larger systems that come from this 27 qubit Falcon processor family, and then also a 65 qubit Hummingbird family. Both of them have this kind of heavy hexagon connectivity that you see on the slide. And they were, from a system building perspective, they were enabled by a couple of critical ingredients. The first, shown on the left under on the Falcon processor, was an advance in the precision with which we can manufacture the components. In particular, their accuracy with which we can control the Josephson energy of the tunnel junction that connects the two islands of the transmine qubit. So these are superconducting processors, right? They use a transmine qubit, which is effectively an LC oscillator, where that inductor, that L, is a nonlinear component, and it's formed by this Josephson junction. And the size of that tunnel barrier is a critical parameter that determines the effective frequency of that nonlinear oscillator. So we really demand, exquisite precision or control over this nonlinear inductance. And the technique that's illustrated in the picture is a post-fabrication annealing process where we can take the distribution shown in red and convert that into the distribution shown in black with a kind of a post-anneal step that's driven through laser activated annealing. On the right, another important ingredient to continue to scale up these systems is to reuse the control components for controlling more than one qubit, rather than having kind of a one-to-one mapping of control hardware to qubits. We need to continue to drive towards a many-to-one mapping, and eventually a logarithmic scaling to retrieve arbitrary scalability. But we've taken the first step at that with our Hummingbird processor by incorporating elements of frequency domain multiplexing in the readout process. So the graph that's shown here is the kind of the spectrum of the linear resonators in the process that are all connected to a common feed line, so that by frequency, by choice of the frequency of the interrogation signal, we can read out individual qubits on a common feed line, and it's equivalent to different channels on your radio station, but now using that same concept in the measurement process. So that's the kind of hardware that these. Sorry, I have a problem with one of my slides. It's animating away from me, and I don't want it to. We'll stick on this and I'll switch back in a second, so I don't have to fix it right now. But so the quantum volume 64 piece, which we did earlier in the year, required a number of different components to work together. So the kinds of circuits that are run in practice, I didn't say much about the structure of these random square circuits, but you can one way to compose these random circuits is that they're alternating layers of an arbitrary element from the SU4 group, followed by an arbitrary permutation network, and those alternate. And so when you write such a circuit in Qiskit, you can see a picture like this, and you have kind of a final layer of measurements at the end. Basically achieving a particular quantum volume result requires executing random instances of circuits of a particular size, and then doing it and then checking that the outputs match the expected outcomes for that random family. And so, for quantum volume 64, there are kind of 4 critical ingredients that went into it. One was a purely software change that we found more efficient ways to decompose these SU4 unitary elements into the basis gates available on the hardware. There was a second component, which is about the basis gates themselves, in particular the 2-qubit gate. On our systems, we've have historically used something known as an echoed cross-resonance gate. And so the cross-resonance interaction, you basically drive one qubit at the frequency, at the transition frequency of a neighboring qubit. And that activates a ZX-like Hamiltonian to drive qubits. It also, unfortunately, though, drives other unwanted or spurious single qubit terms in the control Hamiltonian. And so one of the tricks that we've used for some years now to remove those unwanted terms is to effectively break the interaction in two. So you rotate one direction, use a pi pulse on the control qubit, and then you rotate the opposite direction. And that composite sequence and then echoes away or cancels out some of these unwanted single qubit terms. In this work, though, the team used a kind of dynamic version of that same fundamental idea, something known as rotary echo, to effectively to cancel out those spurious single qubit terms during the drive itself. And so that allowed the team to make the two qubit interaction about 30% shorter in time. And then just from the relative gain of that time versus the coherence times of the qubits, that corresponded to a lower error rate in the fundamental two qubit interaction. There's kind of the more static version of the same idea going on with another compiler change that introduced decoupling pulses in kind of idle slots in the circuit schedule. And then finally, a technique to improve the readout fidelity. The transmine qubit, like I said, is not properly a qubit. It's a nonlinear oscillator, and so that in particular that means that there's more than two states. Right? There's both the ground state and the first excited state, which are what we typically use for the logical 0 and 1 of the effective qubit. But there are higher line states outside of that 0-1 manifold, and in particular. The next highest state, next highest energy state above the first excited state, also couples to our readout process, and it imparts a larger frequency shift on the readout resonator, giving us therefore a larger signal that we can use to distinguish the states. And so that what we effectively did here was use a Schelming process. We use a pi pulse effectively on this 1 to F transition to transfer the population of the 1 state to this F state, and then the standard readout process then can instead of distinguishing between the 0 and 1 responses, is then distinguishing between the 0 and F responses. And that delivers higher readout fidelity. So those were some of the ingredients to get quantum volume 64. To get 128, there was sort of further refinements in several of those components. One, again, back on the software compiler side, that we made the scheduler aware of the error rates of the fundamental gates, and so that in particular durations and errors of the fundamental gates, and that allowed it to find circuits, equivalent circuits of shorter durations, only a few % shorter, but that turned out to be enough. And we made further refinements to the readout process. So these diagrams in the lower right here show you the signal that comes out of the signal processing chain of readout electronics. And in particular, you notice that this isn't just a 0-1 that comes out of the readout system, but is actually a complex number representing the sort of in some ways it is at least proportional to the amplitude and phase of the measurement signal as it is incident on a receiver. And so you have these clusters corresponding to the 0-1 or the 0 and F states when we're using the 6-sided state promotion technique. Previously we used basically a linear decision boundary to separate these two into two classes. But for the quantum volume 128 work, we experimented with a nonlinear decision boundary, in particular just making this decision boundary quadratic. So it sort of skews towards so the blue blob here is the ground state response, and the orange blob is the F state response. And so skewing that decision boundary towards the ground state response was enough to deliver a 7% improvement in the assignment error for the readout. And these two pieces were enough to show quantum volume 128 on the same quantum processor as we had shown quantum volume 64. So further improvements of quantum volume, of course, this is not the end. And like I said earlier, we're really dominated by physical errors. About half of the work that you're seeing here in terms of getting the 6428 step has to do with beating down errors either in the 2-qubit interaction or the readout process, and then making the compiler kind of aware of errors to do better scheduling or better compiling. But really kind of what we expect to be the dominant error or the limiting error in further improvements to quantum volume is this 2-qubit interaction rate, or this 2-qubit error rate. And so that has motivated a flurry of activity within IBM to look at alternative means or alternative approaches to 2-qubit gates with transmons, and ones that are sort of narrow departures from what we're doing now, and ones which are a little bit larger. Sort of the more larger departure column, you can see a result from a manuscript we published earlier this year, looking at a tunable coupler between qubits. So our current processors have a fixed coupling between adjacent qubits. And in this domain, you replace that static interaction with a tunable interaction. And then you drive effectively the coupling rate from this on the coupler, and that's the thing which activates the gate. And the team was able to show error per gates with this kind of scheme that are about down to about 0.1% error per gate. And something which is a sort of a less significant departure from what the systems we're building today. Effectively took a 2-qubit system and modified still in the family of static interactions, but instead of taking just a direct coupler like we have now, sort of combine two different coupling methods. One is a direct coupler and one is a quarter wave resonator that connects them. And these happen to couple with opposite signs. And so that means that there is a sort of a region in frequency space where the static interaction between these qubits actually goes to 0, which removes one of the sort of dominant sources of error in our current family of processors, which is a kind of a ZZ, an unwanted static ZZ interaction between the qubits. And so with this kind of coupling network, again, the team was able to show on a research scale device improvements in error rates, in this case down to about 0.2% error per gate. So, again, there's lots of activity in this domain. It'll be exciting to see what we can achieve in terms of quantum volume when we port any of these improvements from any of these types of approaches into our larger processors, where we can run circuits of sufficient width and depth to show higher quantum volume. So that's a bit I want to tell you about quality. You've perhaps have seen IBM's public messaging about its family of its roadmap of further quantum hardware. I guess that what I wanted to say though today is that in addition to this roadmap, which has predictions about the sort of the size of the systems that IBM intends to build over the next few years, there's kind of a corresponding demand on the kind of error rates that we hope to achieve with these systems, because our intent is really with this Condor scale system, this 1,000-ish qubit system in 2023. We really plan for this to be a test bed for a rich exploration of quantum error correction. And in order to make that feasible, we really need to be, or we want to be in the domain of error rates that are kind of 10 to the minus 4, which should be sufficient to be below threshold for various methods of encoding quantum information in logical qubits. So with that, I think that's perhaps enough on the quality domain. I want to turn though to these other two ingredients of capacity and variety, which I promised you at the beginning, at least in our view, are also critical to actually delivering this frictionless experience. So let's start. It's kind of a motivation why kind of quality is not enough. I think it's necessary to consider or think about a typical workload that you want to run on quantum hardware. What we've noticed looking at a lot of workloads that people are trying to execute today, and even looking back through the history of quantum algorithms, you notice that real quantum workloads are not just quantum circuits. Right? There's actually this interaction that you see over and over again where you have some classical computation that needs to interact with a quantum processor. And so, faithfully executing the complete workload or the complete algorithm really requires efficient interactions between these classical and quantum domains. As we've looked at these kind of workloads, so we've noticed that this interaction doesn't come in just kind of one flavor. There's in fact two different timescales that are relevant for different workloads. One is kind of a real-time interaction, which for superdarking hardware means that this interaction is happening in kind of nanosecond timescales or a few microsecond timescales. And this is a necessary or relevant interaction timescale because these are interactions that need to take place, need to be much faster than the coherence times of the qubits. So this is the domain where error correction, feedback, and feed forward where I need to get data out of the quantum processor and act upon it to steer the course of the circuit while it's executing. There's another relevant timescale though, which we like to label at the near time domain, where it may be acceptable to have slightly longer latencies, maybe millisecond timescales would be acceptable. But where I really want kind of arbitrary compute. In this real-time domain, those latencies of nanoseconds or maybe microseconds are kind of sufficiently demanding that you kind of expect in a real system to operate with certain constraints in that domain, right? It's a very fast interaction, but maybe I don't have very much memory, or maybe I don't have a really high clock speed, or maybe I don't have access to different libraries and so on. Maybe so it's maybe constrained because it has to be so low latency. Maybe it's constrained in other ways. But in this near-time domain, since I'm giving myself a little bit more space in terms of latency, I can really contemplate systems where that compute that I deliver in that space is really rather generic. It's kind of like the full universe of classical computing. And so we want to, because of the constraints and the demands of these different domains, we've proposed to build systems with rather different technologies to solve these two different timescales of the kind of the real-time domain and the near-time domain. So when we look at capacity, what we're really talking about in terms of capacity for executing real workloads is delivering systems that can efficiently execute this quantum classical interactions in that near-time domain. And as kind of a motivational example, I wanted to show you some data from a paper that my colleagues at IBM published a few years ago, looking at using an algorithm of variational quantum eigensolver to measure or to simulate the binding energy for a small molecule. So this is a lithium hydride molecule. And so the team actually did this for the first time in 2017 and then revisited the problem 2 years later in 2019 to show how certain error mitigation approaches could improve the accuracy in terms of simulating this small molecule on near-term hardware. But for connecting this back to the issue of capacity, to collecting the data set for this figure on this page requires, the team actually executed over 4.1 billion circuits, right? So it's really not enough to have a system that can execute just a few circuits. We really need to be able to execute large quantities of it. At the time, we had quantum processors already online, but the team couldn't actually or chose not to execute this experiment with the online tools because back then, were they to try to collect this data set and they made zero errors, they had done, they programmed up exactly the circuits that they needed to run. It would have taken them 45 days to collect the data set that goes into this plot. And that's largely limited by the kind of the quantum classical execution model that was available previously in IBM Quantum Services. So I'll talk about that more in the next few slides. But what's really cool is that we've now built a new system that's called the Qiskit runtime that can execute the same workload in just 9 hours. So there's over 120x speed increase for kind of a real workload. So hopefully you'll see more about the variational quantum eigensolver. You've already seen it during the summer school. If you haven't, kind of the brief, in brief, how this works is that you take your problem, our chemistry problem, and you map that problem onto a Hamiltonian. So something of this form where you have polyterms, a sum of polyterms with weights. And this effectively, for a particular molecule, for instance, represents an operator that is the energy of that molecule. And then you basically need to choose an on-site circuit. So this mapping problem is kind of offline, happens ahead of time. And then when you actually go to run, you take a trial circuit. You have some circuit family that hopefully explores the space, the state space that can populate this operator, this Hamiltonian. So it's a parameterized circuit family, and you prepare trial states and you measure that operator, which corresponds to measuring effectively the energy of that trial state for a particular setting of these parameters theta. And you iterate, you search over that parameter space theta until you find a parameter set that minimizes this energy. And so this exactly has this kind of iterative structure that we were discussing previously, where your classical computer, your classical resource, prepares this parameter vector theta, sends that encoded in a circuit to the quantum hardware. It gets back a set of results, which the classical hardware then can convert into an energy. And with some sort of optimizer, it can pick a new set of parameter values and iterate until it's reached some sort of target accuracy. So that's how the variational quantum eigensolver works. And you can see this kind of interaction then running into the bottleneck of a service like our existing circuit API that we have in IBM Quantum, where if you want to run this kind of problem today with the circuit API, that classical optimization loop and that choosing of circuit parameters and so on happens on your laptop or some sort of classical computer outside of the server itself, right? So out here on your machine, you have this kind of the classical part of this, and your classical component constructs a circuit and sends it to the service where you effectively wait in a queue because you're accessing shared systems. So you have to kind of wait your turn in order to access that resource. When you come out of the queue, we execute it and then push it back to you. So each time you want to go through this loop, there's a hop over the entire internet, and furthermore, a kind of a wait in line in this queuing step. And so, that's kind of probably obvious why it's then slow. In the new model that we built with the Qiskit runtime, instead of interfacing with the service by sending circuits, you interface with the service by sending programs, or you can alternatively request execution of a program that has already been sent. So in this model, right, I'm sending code effectively, or a request to execute code that the service already has. And then the actual generation of the circuits that classical part, which is previously executing on your laptop or something outside of the service, can now execute in a containerized environment co-located with the quantum hardware, where we can make these kind of loops that are necessary for things like the variational quantum eigensolver. We can execute those loops dramatically more efficiently. So what does this actually look like to use this service? We just launched this actually last week. It's in a kind of a limited preview, but we'll be opening it up to more and more users as the year goes on. But you can already, anyone can use the service against a simulator today. The preview is only against actual quantum hardware. But if you want to begin playing with it, you can already do it today. And effectively, what we have today are a set of kind of a fixed set of programs you can interact with, one which is a VQE program. And you effectively construct the inputs to this program and send that off to the service. So to just kind of walk you through this code example for the VQE program, Here, at the top is something which constructs that operator, that Hamiltonian, which is the thing you want to measure. In this particular case, this doesn't correspond to the energy of lithium hydride. This is just some example operator that's short and simple to write down. But of course, like the actual work of submitting a molecule, some of the pre-processing step goes into calculating what the form of this Hamiltonian. You then need a parameterized circuit family that can explore the state space of that Hamiltonian. So here we're using a hardware efficient ansatz. And then you basically bundle up the program inputs, with that ansatz and Hamiltonian. We're going to do an optimization loop. So you got to choose. You can choose from a few optimizers that are built in, and whether or not you want to use measurement error mitigation. So you bundle all those things up into a dictionary, and then you pass it off to the runtime element of the IBM Qiskit provider, and that invokes execution in this environment. You can kind of see what this looks like in practice, of the kind of the new versus the old, where just to collect one data point in that binding energy curve, you have to search over these parameter sets. You can see in the runtime, it takes us about an hour and a quarter to do a few hundred iterations, and 150 hours to get to the same target accuracy with the circuit API. If you notice, right, the number of iterations that we're doing in these two instances is different, and that's an important element in getting the kinds of speed ups that we're reporting here. So I wanted to take a moment to talk about the kind of algorithmic improvement that is also kind of going on under the hood. Kind of part of the difficulty in these kinds of search problems is this optimization element, right? You have to search over parameter space to minimize some operator, and that what the right search strategy is not necessarily obvious, because I'm polling real hardware. I don't necessarily have access to some of the tools you might want to rely upon to accelerate your optimization. So there's been a lot of work in this domain to find better optimization methods. And what we use here is something we've actually just recently published in the last couple of months, that is kind of combines ideas that have been previously proposed in something known as a natural gradient, or quantum natural gradient, that uses kind of the Fisher information matrix to estimate some information about the gradient of your cost function, right? So that any particular choice of the parameters, when I calculate the energy or estimate the energy for that parameter set, I'm effectively sampling some surface where I don't really know, like, if I change the parameters in particular ways, is the energy going to go up or down, other than by trying. But what they do here is effectively they send your circuit and then a modified form of your circuit, which gives them some estimate of kind of the form of the gradient locally. Actually calculating the full gradient is self-expensive, so this is a cheap way that with just sort of one additional step, you can get something which is at least close enough to the gradient, gives you the information about which direction to walk in. And so, like, you can see the impact of this for a synthetic example from this paper, where they looked at the kind of the loss function. This energy estimate is a function of the number of iterations for various different search strategies. And this new one here is the solid green curve for the natural SBSA. And so this sort of gap in kind of the target accuracy versus iteration count is sort of one of the elements here of accelerating lithium hydride example. So kind of the budget of the speed up here is we have this algorithmic improvement from this quantum natural SBSA, which gives about almost a 2x improvement in the total runtime. There's the runtime itself, which gives us about a 4x. And then there's various other changes that we've made to allow us to reduce other overhead, whether it's sort of delays between circuits or the sort of the setup costs and so on. There's also, the hardware itself has gotten better in terms of the gate fidelities and measurement fidelities, which allowed us to actually achieve the same target accuracy with less error mitigation. So all those kind of components added to, kind of multiplied together leads to this massive improvement. And the reason this matters, right, is like if you're actually trying to do experimentation research on these devices, if it's 45 days to ask a single question, you might not even ask the question. But if it's a day or half a day to ask a question, something that becomes something that's actually like tractable, right? I can work with that. And so that it really changes the kinds of problems you can address, or you're going to try to address with real hardware. So finally, let's turn to the aspect of variety. So as I said at the outset, the domain we've been in so far with quantum systems is really the domain of static circuits. And I like to think of static circuits like how kids play dominoes, where they set them up and then you knock them over. Once you set out your course of dominoes and knock the first one over, they fall so quickly it's too late to make any other decisions, right? Like everything's been frozen at that point. The same is true about static circuits. Once you begin executing a static circuit, nothing about it changes. Whereas in a dynamic circuit, you can use measurement to influence what you do in later parts of the circuit. So you might already be familiar with some dynamic circuits, things like quantum teleportation, which some people have suggested is like a hello world for quantum programming, already is itself a dynamic circuit, right? This is something which uses measurements to condition some later classical gates. And of course, quantum teleportation is not just an interesting example of how to use feed forward in a practical sense. It also is relevant for real quantum hardware because the no cloning theorem prevents us from copying quantum data. So if I need to get my quantum data somewhere on the chip to interact with some other register, I really have to move it rather than copy it. And teleportation turns out to be a particularly efficient way to move quantum data over large distances, where I can use prepared resource states to kind of hide some of the cost of moving quantum data around on a chip. We also have other examples that we know about that we can use dynamic circuits to more efficiently prepare large entangled states. It's of course relevant to error correction, where I want to measure some properties of a multi-qubit register, like a parity operator, and I can use some small computation on those parity measurements to find errors in the circuit and correct them. There's also a sort of a growing set of literature that looks at using dynamic circuits for a richer family of operations, things like Clifford operators with dynamic circuits, quantum Fourier transforms, and so on. And so I really think we're kind of at the beginning rather than at the end of discovering what you can really do with dynamic circuits. Our team did one demonstration in the past year that looked at how dynamic circuits compare with the best known static circuits in a phase estimation example. Phase estimation is kind of one of the fundamental ingredients that is used over and over again in a variety of quantum algorithms, all right, which measures the quantum phase of an operator. And there's kind of a well-known example, a well-known algorithm from Kitaev to measure the phase of this operator that uses effectively a large collection of circuits to measure effectively the bits of that phase kind of one at a time. So there's kind of with each one of each pair of circuits like this, you can measure sort of one bit of that phase. There's also, though, a dynamic circuit for the same task of estimating this phase, which effectively reuses an ancillary register to execute the unitary or the operator that you're trying to estimate the phase of over and over again. and resetting it in between each execution. And in this kind of model, you use the measurements that you've executed earlier in time to modify the operations that are happening later. So each one of these conditional Z operations is using the sort of the full data set that's been collected prior in time. And in this way, you can effectively get the entire phase kind of in one shot, where the depth of the circuit now is going to be proportional to the number of bits of precision in that phase estimation. And so what we were able to show, though, is that the dynamic circuit outperforms the static one when you count resources in the same way. So in this particular case, we're counting effectively the number of measurements in the circuit. And you're able to show that the iterative phase estimation circuit has lower error than the entire other static circuit. So this is maybe points towards the potential improvements of dynamic circuits. And of course, one of the things that we need in order to really start exploring the world of dynamic circuits is we need a way to express them. Most quantum systems use some form of quantum assembly language as an input format for describing the circuits. At IBM, we made an effort a few years ago to kind of standardize the kind of growing zoo of quantum assembly languages with something called OpenQASM 2. And what we've done in the last year, though, is propose an extension to OpenQASM, which we're suggesting could be OpenQASM 3.0, which is really focused on this idea of allowing expression of dynamic circuits in quantum assembly languages. So in particular, it has the ability to express kind of extended circuits which can contain arbitrary control flow. So that iterative phase estimation example that we were just talking about in the last slide expresses an OpenQASM program is shown on the right, where you have things like control flow with loop operators like for loops. You have new data types that represent collections of bits. So they can be like an angle type here is this register C, and you have that register C is updated in the loop and then used in this phase operator, this inverse phase operator, which is where that classical data gets used in the feed forward that we saw in the circuit before. There's also some neat concepts to kind of the poll and other things that people have asked for in terms of use of near-term hardware, which is the ability to connect pulse level descriptions to gate level descriptions. You can have an embedded, it allows for embedded pulse descriptions. And there's a mechanism which is inspired by the typesetting algorithm in tech, the boxes and glues concept from tech that allows you to express timing intent in quantum circuits in a flexible and portable way, which you expect to be useful for dynamical decoupling and other error mitigation approaches. Let me wrap up in the last few minutes I've got today to tell you a little bit about the software tools that we're building on top of this platform. I hope many of you have had a chance to check out the Qiskit open source software project. This is a project that is supported by IBM, but is really intended to be platform agnostic. We really want this to work with any hardware and to facilitate both sort of theoretical and experimental study. And it's a sort of a large and growing collection of tools, things like compilers, benchmarking, algorithms, and application modules for things like optimization, chemistry, machine learning, and so on. It even has recently a new component that facilitates hardware design for those that are actually building and designing their own quantum hardware. The one way to think of kind of the universe of packages now in Qiskit is that it's really trying to serve multiple audiences, which we like to think of as kernel developers, those that need the sort of the lowest level access, algorithm developers that sort of don't want to think about dynamic control problems, but the quantum hardware is something which implements an ideal abstraction of gates. And model developers that may not even want to think about circuits so much as they want to think about how to apply quantum computing to some other domain, whether they have subject matter expertise. And if you look at like the kernel and algorithm developers, again, they spend a lot of their time building circuits, and so it's really critical that we have powerful tools to build circuits of different kinds. And so this image kind of represents kind of amalgamation of the various different tools that exist in Qiskit already for building circuits of different kinds. You have things that are really more geared towards the kernel developer, like a pulse description language, which allows you to basically describe the signaling on the individual wires connected to qubits. You have alignment primitives that allow you to introduce timing while still staying at the gate level. In some ways, this connects a lot with what we've introduced with the boxes and springs in QASM 3, Open QASM 3. You have circuit libraries that allow you to think about abstract mathematical objects in like just unitaries and Clifford group operations and be able to compose those. And then things which connect to more algorithmic tasks, where we have a growing library of algorithms such as the quantum Fourier transform, where again, I can just know, we have like quantum Fourier transform, triple adders, Draper adders, and so on, where you can just refer to the kind of the mathematical tasks that you want to perform. And someone else, the library writer, is taking care of the construction of the circuit that executes that task. Finally, if we sort of think about the model developers that kind of sitting on top, we're really trying to build interfaces that that appeal to various subject matter experts, that allow them to make use of quantum hardware at the using terms and language that's already familiar to them. So, like for instance, in the domain of optimization, there's a new Qiskit optimization module, and it's now actually a package. Which allows you to program quantum hardware just by describing an optimization problem. Right? This is real code that describes basically constraint satisfaction, an optimization problem on 3 variables with some subject to some constraints. You basically choose an optimizer and you tell it solve, right? And nowhere in this code do you actually refer to qubits, which is quite curious. And yet this package transforms this optimization problem into a set of circuits, and we can actually execute it. Right, so there's the optimization model is kind of our first step, but we're making similar kinds of packages for chemistry and machine learning and so on. This is all aimed at taking this marvelous technology and in some ways trying to make it disappear, right? To allow people to actually use quantum computers as tools to do real work. And of course, that work today is very much sort of research focused, but we're constantly searching for ways that we might connect the hardware that we can build today and in the near future towards real problems. So with that, I think I'm at the end of my prepared material. I'll go check out your questions.
Hey, Blake. Yeah, let's, it's almost 3:30, so let's, I will ask a few of them from the Q&A. Bilal asks, do you have an estimate for when you will be able to implement error correction?
Great. So I should say that the team is already doing experiments today on error correction. The heavy hex lattice that we've chosen in our Falcon Hummingbird processors, we have schemes, error correction schemes in mind that we've done work on that are sort of a hybrid between a Bacon shortcode and a surface code. We've been doing tests that look at like the syndrome measurements or the check operators, measuring the check operators on real hardware to look at the performance of the system, running real error correction circuits. I guess those systems are not quite large enough to look at sort of the performance as you scale the distance of the code or to do interactions. And so when you have these larger lattices, like with the Osprey and then the Condor systems, we really are looking forward to be able to do sort of a richer set of experience or experiments where we can look at issues of code scaling, where we can look at multi-logical qubit operations and so forth.
Great. Another question, which I think maybe you can take this any way you understand it. How can you use this to train an RBM? I will appreciate a good reference.
You'll have to help me. What is an RBM?
Probably a restricted Boltzmann machine. I think this is a question about QML, maybe, if you
Sure.
want to kind of answer that however you wish to.
I mean, so there's a new Qiskit machine learning package that we just released about a month ago, and there's I don't know that there's tooling in there yet specifically about Boltzmann machines, but any kinds of these network problems that require training depend critically on, like, the efficiency of the training depends on being able to estimate gradients of your circuit with respect to whatever the parameters are. And so one of the things that's important in that package is that it has a gradients framework to effectively take any circuit and give you a new circuit which estimates the gradient of that circuit with respect to whatever parameters. So while I don't know the answer exactly of the difficulty of training a Boltzmann machine, I do know that there's already some tooling in the packages that might assist you in answering the question.
Okay, great. I think let's see. I think there are not too many. Let's see. Nothing else on YouTube. Then I think we should thank Blake for give him a virtual thank you for a fantastic overview of the IBM efforts. And I think I'm personally excited about you know, getting on there and using it. So I think we will